Have you ever looked up at the stars and felt that tug of wonder, that quiet pull toward the infinite? Maybe you've spotted a constellation, traced its shape with your eyes, and felt for a moment like you were part of something vast and ancient. But what if I told you that some of those points of light aren't really where or even what they appear to be? Imagine staring into the deep field of the night sky, only to witness a star that shouldn't be there, or watching as an entire galaxy seems to warp and twist right before your eyes, as if the universe itself were sketching illusions with starlight. This isn't science fiction. This is the cosmic mirage, a breathtaking phenomenon where space doesn't just host reality but actively sculpts it, bending light, warping time, and crafting deceptions so profound they make us question the very nature of existence. In this video, we're setting off on a journey to unravel these celestial mysteries, exploring how gravitational lensing, optical illusions, and other cosmic phenomena conspire to create visions that defy intuition. These aren't mere tricks, they're gateways. Through them, we uncover secrets about the invisible architecture of the cosmos' dark matter, weaving through the void, black holes warping space-time, and forces so subtle yet powerful they guide the evolution of the universe itself. Each illusion is a clue, a piece of a grand puzzle that has captivated astronomers, physicists, and dreamers for generations. This is where science meets the sublime, where what we see is only the beginning of the story. So prepare to have your perspective shifted literally and figuratively. We're about to dive into a world where gravity writes the rules of perception, where light travels billions of years only to arrive as an elegant lie, and where the cosmos reveals its greatest truths through its most captivating deceptions. This is more than a tour of astronomical phenomena. It's an invitation to look deeper, to wonder boldly, and to rediscover just how astonishing and mysterious our universe truly is. Think about the last time you saw a rainbow after a storm. Those beautiful bands of color aren't actually a physical object you could ever fly to. They're an illusion created by sunlight bending through countless water droplets, each one acting like a tiny prism. In many ways, the entire universe operates on a similar principle of deception, but on a scale so vast it's almost impossible to comprehend. The light that reaches our eyes and our telescopes is not a simple, straightforward telegram from the cosmos. It's more like a message that has been passed through a series of funhouse mirrors, each one twisting and distorting the original information. This journey begins with the very nature of light itself. It travels across the unimaginable void for millions, even billions of years, carrying with it the secrets of distant stars and ancient galaxies. But its path is never a perfect straight line. The vacuum of space isn't truly empty. It's filled with the invisible influence of gravity, and this is where the magic, or rather the physics, truly happens. According to Einstein's revolutionary theory of general relativity, gravity isn't just a force that pulls on objects. It's actually a warping of the very fabric of space and time. Imagine placing a heavy bowling ball in the center of a stretched-out rubber sheet. The sheet would dip dramatically. Now, roll a few marbles across that curved surface. Their paths would bend around the central weight, not because they're being pulled by a force in the classical sense, but because they're simply following the curved geometry of the sheet. Light behaves in exactly the same way. Even though it has no mass, a beam of light travels through the warped spacetime around a massive object like a galaxy or a black hole, and its path curves. It doesn't speed up or slow down. It just changes direction, following the cosmic contour lines. This means that when we observe a distant star whose light has skimmed past a massive galaxy cluster on its way to us, we might see it in a completely different location than where it actually resides. Sometimes the bending is so severe that we see multiple copies of the same object, or it appears as a stretched-out arc or even a complete ring of light. This manipulation of light creates a fundamental disconnect between perception and reality. Our telescopes are incredible time machines, showing us the universe as it was in the distant past, but they are also unwitting victims of this grand cosmic illusion. They collect the light that arrives after its long and twisted journey and present it to us as a direct image. They cannot tell us on their own that the star we're looking at is actually far to the left of where it appears, or that the strange, glowing ring is actually a single quasar billions of light years behind a foreground galaxy. We are, in a very real sense, seeing a universe that has been edited and rearranged by gravity itself. Unraveling this illusion requires us to become cosmic detectives, using our understanding of physics to reverse engineer the light's journey, to subtract the distortions, and to finally glimpse the true architecture of the cosmos hidden behind the mirage. It all started with a radical idea from a mind that dared to rethink the universe. In 1915, Albert Einstein published his general theory of relativity, a framework that completely upended our understanding of gravity. He proposed that what we perceive as gravity isn't a force in the traditional sense, but rather a curvature in the very fabric of space-time caused by mass and energy. A planet, a star, or a galaxy doesn't just sit in space. It bends the stage upon which everything else performs, and just like a marble would roll along the curved surface of a trampoline with a bowling ball in the center, anything moving through this warped space-time, including light, will have its path altered. This was the profound prediction that the light from a distant star, as it grazed the limb of our sun, would be deflected by a tiny but measurable amount. At the time, this was a staggering, almost unbelievable claim. Light was thought to travel in perfectly straight lines, and the notion that its path could be bent by an invisible geometric curvature was a concept so foreign it was initially met with skepticism, even by Einstein himself. He saw it first and foremost as a crucial test for his theory. The opportunity to prove it came during a total solar eclipse in 1919, when Sir Arthur Eddington led an expedition to photograph the stars appearing near the sun's darkened limb. The measured positions of those stars were indeed shifted, exactly as Einstein's equations had foretold. This validation made him a global celebrity overnight, but the deeper implication, that entire galaxies could act as colossal cosmic lenses, was still seen by many as a mathematical oddity, a theoretical flourish with little practical application in astronomy. For decades, the concept remained largely in the background, a fascinating footnote in physics textbooks. Astronomers knew it must be happening on grand scales, but detecting it required a specific and rare cosmic alignment. A massively luminous object like a quasar positioned almost perfectly behind a massive foreground object like a galaxy. It wasn't until 1979 that this precise celestial lineup was found. Astronomers discovered what appeared to be twin quasars, two identical, incredibly bright objects side by side in the sky. After meticulous study, they realized they weren't looking at two distinct objects, but two images of the very same quasar. Its light had been split into separate paths by the gravitational field of an intervening galaxy, creating the first confirmed example of a strong gravitational lens. This was the moment the field was truly born, transforming Einstein's theoretical prediction into an observational powerhouse. Today, gravitational lensing is far from a curiosity. It is an indispensable tool in the modern astronomer's kit. Its applications are as diverse as they are profound. By carefully measuring the distortion of background galaxies, a subtle effect known as weak lensing, scientists can literally map the distribution of dark matter in massive galaxy clusters. They can trace its invisible halo, revealing how this mysterious substance vastly outweighs the visible stars and gas. In other cases, lensing acts as a natural telescope, a phenomenon called cosmic magnification. The gravity of a foreground cluster can amplify the faint light from incredibly distant galaxies lying behind it, allowing us to peer further back in time than ever before and study the formation of the very first generations of stars. Perhaps the most visually striking example is the Einstein ring, a perfect or nearly perfect circle of light. This breathtaking illusion occurs when the source, the lens, and the observer are in perfect alignment. The light from the background object is smeared and stretched by gravity into a luminous halo, a direct and beautiful manifestation of the warped geometry of space. Each ring is not just a pretty picture, it's a precise cosmic scale. By analyzing its properties, astronomers can accurately weigh the lensing galaxy, providing one of the most reliable methods for determining mass across the universe. From an unintended consequence of a grand theory to a cornerstone of modern cosmology, gravitational lensing stands as a brilliant testament to a powerful truth. Sometimes, the universe's most clever deceptions are the very things that reveal its deepest secrets. Now that we understand how gravity can bend the path of light, let's explore the different ways this cosmic trickery actually shows up in our telescopes. Astronomers have categorized gravitational lensing into three main types, each with its own distinct signature and scientific superpower. The most dramatic and visually stunning of these is known as strong gravitational lensing. This is what most people picture when they think of the phenomenon. It occurs when the alignment between a distant light source and a massive foreground object, like a galaxy cluster, is exceptionally precise. The gravitational field is so intense and so perfectly positioned that it doesn't just slightly nudge the light, it completely reshapes it. The results are the breathtaking cosmic mirages we see in so many Hubble images, multiple, sharp images of a single quasar arranged in a cross-like pattern, or the spectacular Einstein rings, those perfect, luminous halos that form when a background galaxy is smeared into a complete circle around the lensing cluster. These aren't just beautiful accidents, they are incredibly precise tools. By studying the exact geometry of these multiple images and arcs, astronomers can perform a kind of cosmic weigh-in, calculating the total mass of the foreground cluster with remarkable accuracy. But strong lensing events are relatively rare, requiring that perfect needle-in-a-haystack alignment. Far more common, though much more subtle, is the effect known as weak gravitational lensing. In these cases, the distortion is not severe enough to create multiple images or rings. Instead, the gravity of a large-scale structure, like a filament of dark matter or a less massive galaxy group, imposes a slight but coherent distortion on the shapes of thousands of background galaxies. Imagine looking at a field of distant, faint galaxies. Without any lensing, their orientations would be random, a chaotic sprinkle of ovals and spirals pointing in every direction. But if a massive but invisible clump of dark matter lies between them and us, its gravity will very slightly stretch and shear the light from those background galaxies, making them all appear just a tiny bit aligned, as if they're all stretching in a preferred direction. The effect on any single galaxy is minuscule, almost imperceptible, but by measuring the collective, statistical alignment of thousands upon thousands of galaxies, powerful computers can map the invisible gravitational field that caused it. This is how weak lensing has become our premier method for creating vast three-dimensional maps of the dark matter web that forms the hidden skeleton of our universe. The third type brings the phenomenon down to a much more personal, stellar scale, microlensing. Here, the lens isn't a gigantic galaxy cluster but a single star or even a planet drifting through our galaxy. The principle is the same, but the effect is transient and doesn't involve distortion of shape. Because the lensing object is so small, it doesn't create multiple images. The separation between them is so tiny that our telescopes cannot resolve them. Instead, what we see is a temporary brightening, as a faint background star and a dim foreground object like a brown dwarf or a Jupiter-sized planet align from our viewpoint on Earth. The gravity of the foreground object acts as a magnifying glass, focusing the light of the background star and causing it to briefly flare in brightness. This flare follows a very specific and predictable pattern, a smooth, symmetric rise to a peak as the objects align, followed by an identical decline as they move out of alignment. The entire event might last for hours, days, or weeks. The beauty of microlensing is its ability to reveal objects that emit no light whatsoever. It has become one of the most successful techniques for finding rogue planets, worlds untethered to any star, drifting alone in the interstellar darkness, as their gravity betrays their presence when they pass in front of a more distant star. So while strong lensing gives us these spectacular, poster-worthy images that allow us to weigh massive clusters, and weak lensing allows us to chart the invisible dark matter cosmos, microlensing operates on a human timescale, providing a unique census of the faint and forgotten objects, the lone wanderers of our galaxy that would otherwise remain completely invisible to us. Together, these three flavors of gravitational lensing provide a complete toolkit, allowing astronomers to probe the universe's structure from the largest scales of dark matter down to the smallest, darkest worlds. Among the countless wonders revealed by gravitational lensing, few are as perfectly illustrative and visually striking as the phenomenon known as the Einstein cross. Picture this: a relatively ordinary-looking galaxy, a fuzzy smudge of billions of stars, sits quietly in the center of the frame. But encircling it, arranged with an almost unnatural symmetry, are four brilliant blue-white points of light. They form a perfect cross, a celestial pattern so precise it seems almost designed. The astonishing truth is that those 4 points are not 4 separate stars or galaxies. They are 4 separate images of the exact same object, a single, ferociously energetic quasar located billions of light-years behind the central galaxy. This incredible mirage is a textbook example of strong gravitational lensing pushed to its most elegant extreme. It occurs only under a very specific set of cosmic circumstances. The quasar, an incredibly luminous active galactic nucleus powered by a supermassive black hole greedily consuming matter, must lie almost directly behind the center of the foreground galaxy from our precise vantage point here on Earth. The gravity of this intervening galaxy is so immense that it warps the space-time around it into a complex lens. The light from the distant quasar traveling toward us is forced to navigate this warped landscape. Instead of taking a single, straight line path, the light splits, traveling along multiple different routes around the galaxy. Each path delivers a complete image of the quasar to our telescopes, but from a slightly different angle, creating the stunning cross pattern we observe. It's as if the galaxy is a complex jewel, a cosmic diamond, with facets that each reflect a separate image of the same brilliant background source. The discovery of the first Einstein cross in 1985, officially designated Q2237+0305, was a monumental moment in observational astronomy. For decades, the effect had been a purely theoretical prediction, a beautiful consequence of Einstein's math that many doubted we would ever be lucky enough to see in such a pristine form. Finding it was like discovering a perfect natural archetype, a Rosetta Stone for decoding gravitational lensing. It provided the most direct and undeniable visual proof that massive objects could bend light in precisely the way general relativity had predicted 70 years prior. But the Einstein cross is far more than just a pretty confirmation of an old theory. It is a dynamic cosmic laboratory that continues to yield new discoveries. Because the light in each of the four images has traveled a different path, each route is a slightly different length. This means that if the quasar at the heart of it all suddenly flares in brightness, which these volatile objects are known to do, that flare won't appear in all four images at the same time. It will appear in one, then another, with a delay of hours or even days between them. By meticulously tracking these time delays, astronomers can perform a remarkable feat of cosmic triangulation. They can measure the exact differences in the path lengths the light has taken, which in turn allows them to calculate the precise mass of the foreground lensing galaxy, including all of its invisible dark matter. It's like using the flickering of the mirage itself to weigh the object creating it. Furthermore, the cross provides a unique opportunity to study the quasar itself in incredible detail. The lensing galaxy's magnification effect acts as a natural telescope, boosting the quasar's light and allowing scientists to probe its structure and environment in ways that would be utterly impossible without this gravitational assist. They can study the clouds of hot gas swirling around the central black hole, measure magnetic fields, and test models of how these incredible engines operate. The foreground galaxy gets its share of scrutiny too. By analyzing how it bends the light, astronomers can map the distribution of matter within it, discerning how its mass is arranged from its bright core to its vast dark halo. A single, seemingly simple trick of the light thus becomes a powerful tool for investigating two vastly different cosmic structures simultaneously. The Einstein cross stands as a permanent testament to the idea that in the cosmos, the most beautiful illusions often hold the most valuable truths. While gravitational lensing shows us how gravity can bend the very light we see, another prediction from Einstein's theory reveals an even more fundamental kind of distortion, one that doesn't just alter the path of light, but warps the stage upon which everything unfolds. These are gravitational waves, ripples in the fabric of spacetime itself, generated when massive objects undergo violent acceleration, like two black holes spiraling inward and merging in a final, spectacular collision. Unlike light which travels through space, gravitational waves are vibrations of space. As they pass through the cosmos, they literally stretch and compress the dimensions of reality, momentarily changing the distance between objects and even the flow of time. It's as if the universe itself is breathing, expanding and contracting in a rhythm set by its most cataclysmic events. For decades, these waves remained entirely theoretical, a beautiful mathematical consequence of general relativity that even Einstein himself doubted we would ever detect. The distortions they create are almost unimaginably tiny. A powerful gravitational wave passing through Earth might change the distance between two objects 4 kilometers apart by less than 1,000th the width of a proton. Detecting such a minuscule signal seemed like science fiction. That all changed on September 14, 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first historic detection. The signal, designated GW150914, was a faint chirp that lasted just 0.2 of a second, but it told an incredible story, the final moments of two black holes, each about 30 times the mass of our Sun, colliding over 1 billion light-years away. In that instant, a portion of their combined mass was converted into pure energy and radiated away as gravitational waves, rippling outward across the universe at the speed of light until they finally reached us, forever changing astronomy. So how do these ripples play tricks on our perception? Imagine two free-floating objects in space. As a gravitational wave passes by, the space between them will rhythmically stretch and squeeze. If you were standing next to them, you wouldn't feel anything yourself because everything, including your own body and your measuring tools, would be distorting in exactly the same way. It's a change in the geometry of the universe itself. Now consider what this means for light. A beam of light traveling through space that is being alternately compressed and expanded by a passing gravitational wave will have its wavelength subtly altered. This means that in principle, these waves could create their own form of cosmic mirage, not by bending the path of the light, but by minutely shifting its color or its timing as it journeys toward us. While we don't see this effect as a visual distortion like an Einstein ring, it represents a deeper, more fundamental kind of illusion, where the very rules of measurement are temporarily rewritten by the universe. The study of these waves has opened an entirely new window on the cosmos, one that doesn't rely on light at all. This is the era of multi-messenger astronomy. We can now listen to the vibrations of spacetime to hear events that are completely dark to traditional telescopes, like the mergers of black holes. In 2017, this new sense delivered its most spectacular result yet. LIGO, along with its European counterpart Virgo, detected gravitational waves from the collision of two neutron stars. Crucially, this event was also seen by telescopes across the globe and in space, which observed the brilliant flash of gamma rays and the glowing kilonova that followed, a cosmic forge where heavy elements like gold and platinum are created. For the first time, we could both hear the spacetime ripples and see the light from the same event, providing a stunningly complete picture of a violent cosmic transformation. This new ability to listen to the universe is revealing a hidden symphony of activity, from the gentle hum of distant, merging black holes to the violent crashes of dense neutron stars. Each detection is like adding a new instrument to the orchestra, allowing us to perceive the cosmos not just as a silent, beautiful painting, but as a dynamic, vibrating, and ever-changing entity. Gravitational waves remind us that reality is not a static stage but a flexible, living fabric, constantly being reshaped by the most powerful events in creation. They are the ultimate testament to the fact that the universe's greatest tricks are not just visual, they are woven into the very essence of space and time. So if gravity is the artist that sculpts these cosmic mirages, what exactly is providing the raw material, the invisible clay? For decades, we've known that the gravity we can see, from stars, galaxies, and glowing gas, is simply not enough to hold the universe together. The math didn't add up. Galaxies were spinning so fast that they should have flown apart long ago, and giant clusters of galaxies didn't contain nearly enough visible matter to generate the gravitational glue keeping them bound. There had to be something else, something massive yet entirely unseen. This missing ingredient is dark matter, a substance that makes up roughly 27% of the entire cosmos. Unlike anything we are familiar with, it does not interact with light at all. It doesn't shine, reflect, absorb, or block it. It is completely and utterly dark, detectable only through its profound gravitational pull on the things we can see. And it is this invisible substance that acts as the primary architect, the master builder of the universe's largest structures and, consequently, its most dramatic illusions. Think of a massive galaxy cluster, one of the largest gravitationally bound structures in existence. When we look at it with our most powerful telescopes, we see thousands of brilliant galaxies swirling in a vast sea of hot, glowing gas. But this spectacular visible display is merely the glittering decoration on the surface of something much deeper and far more massive. The true bulk of the cluster, as much as 90% of its total mass, is in the form of an immense, invisible sphere of dark matter, a halo that envelops the entire cluster and extends far beyond its visible edge. This dark matter is the hidden scaffolding, the underlying framework that dictates how the entire structure holds together, and most importantly for our story, how it bends the fabric of space-time. This is where gravitational lensing becomes our most powerful detective tool. When astronomers train their telescopes on a massive cluster, they don't just look at the bright galaxies within it. They also carefully study the faint, distorted images of the even more distant galaxies that lie billions of light years behind it. The light from these background galaxies must pass through the cluster's immense gravitational field on its way to us. By meticulously mapping the precise distortions in these background galaxies, how they are stretched into faint, elongated arcs or smeared into intricate patterns, scientists can perform a remarkable feat of reverse engineering. They can calculate exactly how much mass must be present in the foreground cluster to cause that specific warping of light. And time again, the result is the same. The amount of mass required to create the observed lensing effect is 5 to 10 times greater than the mass of all the visible stars and gas combined. The only explanation is that the majority of the mass is in the form of this invisible dark matter. Perhaps the most stunning and conclusive evidence for this comes from observations of colliding galaxy clusters, like the famous Bullet cluster. Here, two massive clusters have smashed into each other in one of the most energetic events since the Big Bang. The visible components, the galaxies themselves, and the hot gas between them behave differently during this collision. The galaxies, relatively small and spaced far apart, largely pass through one another like two swarms of bees. The clouds of hot gas, however, are much more like a fluid. They slam into each other, slow down, and become separated from the galaxies. But when astronomers map the mass using gravitational lensing, they find something astonishing. The peak of the total mass, the true gravitational core of the system, does not lie with the slowed-down gas, which is the brightest, most visible part. It doesn't even perfectly align with the galaxies. Instead, the lensing map reveals that the majority of the mass has also sailed right through the collision, completely unaffected, and is now located in two clear clumps far away from the gas. This is the signature of dark matter. It interacts only through gravity, so during a collision, it simply doesn't see the other matter and keeps on moving, revealing its presence through the very mirages it creates. Without this dark matter scaffolding, the universe would be a very different and far less interesting place. The gravitational lensing effects we rely on to study the early cosmos would be dramatically weaker if they existed at all. There would be no massive enough clumps of matter to create the breathtaking Einstein rings or the multiple images of distant quasars. The cosmic magnifying glass would be far too weak to bring the earliest galaxies into view. Dark matter, by its very absence from the electromagnetic spectrum, is the unseen hand that sculpts the light we see. It warps the stage of space-time so severely that it creates these magnificent deceptions, these cosmic mirages that are not just beautiful accidents, but the very clues that allow us to deduce its existence, map its distribution, and begin to understand the hidden architecture of everything. If gravitational lensing gives us cosmic mirages and dark matter provides the invisible scaffolding, then black holes are the master illusionists themselves, warping reality to such an extreme that the very laws of physics seem to break down. These enigmatic objects, born from the collapse of the most massive stars, possess a gravitational pull so intense that not even light can escape their clutches once it crosses a point of no return known as the event horizon. It is this absolute dominion over light that makes them the ultimate cosmic deceivers, crafting a menagerie of visual paradoxes that challenge our fundamental understanding of space and time. Consider the simple act of observing a black hole. What do you actually see? Since no light can come out, a lone black hole against the empty void of space would be utterly invisible, a perfect paradox of immense presence and total absence. But nature rarely presents them in isolation. Often, they are surrounded by a frenzied, luminous disk of superheated gas and dust, known as an accretion disk, which spirals inward at near light speed, glowing brilliantly across the electromagnetic spectrum. It is against this bright backdrop that the black hole's gravity performs its most famous trick. It bends the light emanating from behind it, wrapping it around its form to create a dark, central shadow encircled by a thin, bright ring of light. This is the black hole's silhouette, an illusion crafted from distorted light that was never actually emitted by the black hole itself. The now iconic image of the supermassive black hole at the heart of the galaxy M87, released in 2019, is a stunning portrait of this very phenomenon, not a direct picture of the black hole, but a photograph of its gravitational influence, a shadow play on a cosmic scale. Venture even closer to the event horizon, and the illusions become even more bizarre. According to the equations of general relativity, there is a distance from a black hole where gravity is so strong that photons of light can be forced into temporary stable orbits. This region is called the photon sphere, a shell of space where light itself circles the black hole like a satellite. It is an utterly unstable region. A photon there could, in theory, loop around forever, but the slightest perturbation would send it either spiraling inward to its doom or flying outward into the universe. From our distant perspective, this creates the effect of a perfect, razor-thin ring of light seemingly hovering impossibly around the black hole's shadow. But the deception runs deeper, because light can orbit here. What we perceive is a chaotic hall of mirrors. The light from a single star behind the black hole could loop around once, twice, or even multiple times before escaping toward us. This would create not just 2 or 4 images of that star, as with a galactic lens, but an infinite series of increasingly faint and distorted copies, nestled within the ring of the photon sphere itself. It's a visual echo chamber generated by gravity's ultimate grip. The gravitational lensing around a black hole doesn't stop at creating multiple images. It can warp our entire view of the cosmos behind it. Imagine a background galaxy located directly behind a black hole from our line of sight. The black hole's immense gravity would bend the galaxy's light all around itself, smearing it not into a simple arc, but into a complete or almost complete Einstein ring that appears to encircle the black hole's shadow. As the black hole moves through space or rotates, this ring can appear to shift, twist, and morph, making it seem as if entire galaxies are swinging in a dizzying dance around a central point of darkness. This isn't just a static illusion. It's a dynamic, real-time distortion that depends on the black hole's spin and our viewing angle. For a rapidly spinning Kerr black hole, the effects are even more pronounced, dragging the very fabric of space-time around with it and twisting these light rings into complex, pretzel-like shapes. Yet, for all their trickery, these illusions are a gift to science. By carefully studying the precise size and shape of the black hole's shadow and the rings of light around it, astronomers can perform precise measurements of its fundamental properties. The diameter of the shadow is directly related to the black hole's mass, providing a powerful scale for weighing these invisible giants. The distortion and asymmetry of the surrounding light reveal the black hole's spin, telling us how fast this cosmic engine is rotating. Every photon that has traveled along these warped paths carries with it encoded information about the geometry of space-time in the most extreme environment possible, allowing us to test general relativity in a regime where it truly flexes its muscles. The master deceivers, through the very illusions they create, are ultimately revealing their deepest secrets. While black holes and dark matter sculpt the cosmic stage with their immense gravity, there exists another, far more enigmatic force working on the largest scales imaginable, one that doesn't pull matter together but relentlessly pushes it apart. This is dark energy, the mysterious driver behind the accelerating expansion of our universe. Its influence is more subtle than the dramatic warping of a black hole, but it weaves a profound and pervasive illusion that fundamentally alters how we perceive and interpret every cosmic mirage we observe. To understand its deceptive power, we need to reimagine the very canvas upon which these light-bending events are painted. Think of the universe not as a static stage, but as an ever-expanding sheet of elastic fabric. Every galaxy, every cluster is a point on this sheet. Dark energy is the invisible hand that stretches this fabric, causing every point to move away from every other point at an ever-increasing rate. Now consider a gravitational lensing event, a massive galaxy cluster bending the light from a more distant quasar to create a beautiful Einstein ring. The properties of that ring, its size, its brightness, the precise time delays between its multiple images depend critically on the exact distances involved. We need to know how far away the lensing cluster is and how far away the background quasar is to accurately calculate the mass of the cluster and the true nature of the quasar. But if the fabric of space itself is stretching while the light is in transit, those distances are not fixed. They are moving targets. This is where dark energy inserts its most clever trick. It changes the geometry of the universe's expansion over time, which in turn changes how we measure cosmic distances. The formulas cosmologists use to calculate the space between objects, known as the distance-redshift relation, are directly influenced by the amount and behavior of dark energy. If we were to mistakenly assume a universe without dark energy, one that expands at a constant or decelerating rate, we would severely miscalculate the distances to both the lensing object and the source. This miscalculation would then throw off every single deduction we make from the mirage. We might overestimate or underestimate the mass of the lensing cluster. We might misinterpret the intrinsic brightness of the background quasar. The entire beautiful, precise measurement becomes skewed because the ruler we used to measure the scene was itself stretching in a way we failed to account for. The mirage is real, but our interpretation of it becomes an illusion crafted by dark energy. Furthermore, dark energy's repulsive force acts as a counterweight to gravity's attractive pull on the largest scales. Over the eons, as dark energy becomes the dominant component of the universe, it increasingly suppresses the growth of the very large-scale structures, the galaxy clusters and dark matter halos, that act as the most powerful gravitational lenses. In a universe dominated by gravity, these structures would continue to grow ever larger and more massive, creating stronger and more frequent lensing events. But dark energy puts a brake on this process. It makes it harder for matter to clump together, potentially leading to a future universe where strong gravitational lenses, those spectacular Einstein rings and crosses, become rarer and weaker. The cosmic magnifying glass, in a sense, begins to lose its power. This means that the abundance and strength of the gravitational mirages we see today are not just a snapshot. They are a fossil record of the battle between gravity and dark energy throughout cosmic history. By meticulously studying populations of gravitational lenses across vast distances, and thus looking back in time, cosmologists can actually use these mirages to probe the nature of dark energy itself. Different theoretical models for dark energy predict different expansion histories for the universe. By counting how many strong lenses exist at different epochs and measuring their properties, astronomers can determine which expansion history best fits the data. It turns the illusion into a tool. The very distortions that dark energy makes possible become the means by which we uncover its secrets, helping us refine our models for the ultimate fate of the cosmos, whether it ends in a perpetual acceleration, a gradual slowdown, or something even more strange. So while it doesn't bend light directly, dark energy warps our entire frame of reference. It manipulates the cosmic distances that are fundamental to our understanding. It influences the growth of the structures that create the lenses, and it quietly dictates the evolution of the universe's deceptive potential. It reminds us that to truly see through a cosmic mirage, we must first understand the hidden properties of the expanding space through which the light has traveled for billions of years. While the grand distortions of gravitational lensing are orchestrated by the immense gravity of dark matter and black holes, a far more local and familiar set of illusions can trick our eyes and instruments right here from Earth. Our own atmosphere, that thin protective blanket that makes life possible, is also a constant source of astronomical deception. As starlight enters this turbulent sea of moving air, it passes through pockets of varying temperature and density. These pockets act like countless shifting lenses, each one bending the light by a tiny amount. The cumulative effect is the beautiful, romantic twinkle of the stars, a phenomenon known as astronomical scintillation. But this twinkle is more than just a poetic feature of the night. It's a form of image degradation. It blurs fine details, smears out point sources, and causes the apparent position of a star to jitter slightly. For astronomers trying to take razor-sharp images or make precise positional measurements, this atmospheric turbulence is a formidable adversary that must be overcome with advanced technology like adaptive optics, which uses a laser guide star and a deformable mirror to counteract the blurring in real time, effectively cancelling out the atmosphere's illusion. Beyond simple twinkling, the atmosphere can create more dramatic mirages. A powerful example is atmospheric refraction, the same effect that causes a spoon in a glass of water to look bent. When a star or planet is located very close to the horizon, its light must travel through a much thicker slice of atmosphere to reach us. This dense air bends the light upward, making the celestial object appear slightly higher in the sky than it actually is. In extreme cases, this can create breathtaking effects like the famous green flash observed just as the sun sets over the ocean, where the last sliver of the solar disk appears to shimmer with an emerald hue as different colors of light are refracted by different amounts. These phenomena are not flaws in the universe's design, but beautiful reminders that our perception is always mediated by the environment we observe from. The tools we build to extend our vision can also introduce their own unique deceptions. Every telescope and camera is a complex instrument with physical limitations. Sometimes the light entering them can bounce around internal surfaces or be diffracted by the support structures holding a secondary mirror, creating artifacts, false features that aren't really out there in space. A bright star might appear to have faint, spiked rays emanating from it, but those are often just diffraction spikes from the telescope's own design. Glints of stray light can create lens flares that mimic the appearance of unidentified objects. Perhaps the most famous instrumental illusion occurred in the early days of radio astronomy, when researchers Jocelyn Bell Burnell and Anthony Hewish detected a persistent, incredibly regular signal pulsing from deep space. Their first cautious name for it was LGM-1 for Little Green Men, as the signal's artificial seeming precision was so unlike any known natural phenomenon. It turned out, of course, to be the first discovery of a pulsar, a rapidly spinning neutron star, and not a galactic greeting card. This story highlights a critical point in science. The line between a groundbreaking discovery and a simple instrumental error or misinterpretation can be incredibly fine, and the most rigorous skepticism is required to tell them apart. Then there is the trickster that resides not in our instruments or our atmosphere, but within our own brains, pareidolia. This is the innate human tendency to perceive familiar patterns, especially faces, in random or ambiguous data. It's the psychological mechanism behind seeing animals in clouds or a man in the moon. Astronomy is rife with famous examples. In 1976, a Viking orbiter image of a Martian hill bore an uncanny resemblance to a human face, sparking decades of speculation about ancient alien civilizations. Higher resolution images taken decades later confirmed it was merely an interestingly eroded mesa, a trick of light and shadow upon rock. Similarly, people have seen everything from a cosmic hand of God in a nebula to a space crab in the remnants of a supernova. These illusions are not scientifically significant in themselves, but they are culturally and psychologically fascinating. They reveal our deep-seated desire to find meaning and familiarity in the vast, impersonal cosmos. They also serve as an important cautionary tale, reminding scientists and the public alike to apply careful analysis before jumping to extraordinary conclusions based on shape alone. Ultimately, this entire spectrum of illusions, from atmospheric twinkling to the mind's own pattern-making, teaches a humbling lesson. The quest to understand the universe is a constant process of peeling back layers of deception. We must account for the distortions of our atmosphere, calibrate out the artifacts of our instruments, and be mindful of the biases hardwired into our own perception. Distinguishing a true cosmic signal from a mere trick of light or mind is the very essence of the scientific process. It demands meticulous observation, independent verification, and a healthy dose of skepticism. These earthly and psychological mirages may lack the cosmic grandeur of an Einstein ring, but they are just as important to understand, for they define the boundary between what we see and what is truly there. To truly grasp the monumental leap forward that the Hubble Space Telescope provided, we have to recall the state of astronomy before it left the confines of our planet. Ground-based observatories, for all their power, were perpetually looking up through a watery, turbulent veil. Our atmosphere, so essential for life, is the natural enemy of the astronomer seeking pristine, stable images. It smears starlight, blurs fine details, and causes the familiar twinkle that, while romantic, is a form of visual noise. For a phenomenon as subtle and intricate as gravitational lensing, where the goal is to measure the most minute distortions in the shapes of incredibly distant and faint galaxies, this atmospheric interference was a crippling limitation. Theories about cosmic mirages were robust, but the observational evidence was often fuzzy, ambiguous, and open to debate. We knew the universe was playing tricks, but our view of the magic show was from the very back row of a very smoky theater. Then, on April 24, 1990, the Space Shuttle Discovery carried Hubble into orbit, and the roof of that theater was effectively blown off. By positioning itself high above the distorting effects of the atmosphere, Hubble didn't just get a clearer view, it gained an entirely new sense of sight. Its vision was immediately and stunningly sharp, capable of resolving details with a clarity that was previously unimaginable. For the study of gravitational lensing, this was nothing short of a revolution. Suddenly, the theoretical curiosities and faint hints seen from the ground were transformed into breathtaking, incontrovertible reality. Hubble's images didn't just confirm that Einstein rings existed. They rendered them in such exquisite detail that scientists could use them as precision instruments. One of Hubble's most profound contributions came through its deep field observations. By staring at a single, seemingly empty patch of sky for days on end, it collected the faint light of thousands of galaxies billions of light years away. In these incredible deep fields, the phenomenon of weak gravitational lensing, once nearly impossible to detect from the ground, became a ubiquitous feature. Hubble's sharp eyes could discern the tiny, coherent distortions in the shapes of countless background galaxies. They weren't randomly oriented. Their slight elongations pointed like faint compass needles toward the unseen gravitational influence of dark matter filaments weaving through the cosmos. This allowed astronomers to move from merely proving dark matter exists to actually mapping its vast, invisible architecture in 3 dimensions. Hubble turned the entire sky into a canvas where the hidden mass of the universe revealed itself through the subtle warping of light. Of course, it was the strong lensing events that produced the most iconic poster-worthy images. Hubble captured galaxy clusters like Abell 168 and the Bullet Cluster not as simple collections of galaxies, but as immense natural lenses, their gravitational fields sculpting the light from background galaxies into long, delicate arcs and multiple images. These weren't just beautiful pictures, they were data-rich maps. By analyzing the precise curvature of these arcs and the positions of the mirrored images, astronomers could perform a kind of cosmic accounting, adding up the total mass in the cluster. Time and again, the result was the same. The mass required to create such dramatic bending was 5 to 10 times greater than the mass of all the visible stars and gas combined. Hubble's visuals provided the most powerful Chinese letter intuitive evidence for the dominance of dark matter. The telescope's longevity also proved to be a key asset. Gravitational lensing is not always a static illusion. For those rare and precious alignments where the background object is a variable quasar, the light travel time along each distorted path is slightly different. This means a flare in the quasar's brightness will appear in one mirrored image days or weeks before it appears in another. Hubble's ability to monitor these systems over years allowed astronomers to measure these time delays with exquisite precision. These measurements are like cosmic stopwatches. They provide the critical timing data needed to reverse engineer the geometry of the entire system, yielding independent measurements of the universe's expansion rate and offering crucial insights into the nature of dark energy. Perhaps Hubble's greatest legacy in this field is how it transformed gravitational lensing from a rare astronomical oddity into a standard tool for exploration. It didn't just find a few spectacular examples, it revealed that these mirages are everywhere once you have the clarity to see them. Its vast archive of images, a treasure trove accumulated over 3 decades of service, continues to be mined by scientists and even citizen scientists for new and ever more complex lensing systems. The Hubble Space Telescope took the universe's most elaborate deceptions and, by capturing them with unparalleled beauty and precision, turned them into one of our most reliable guides for understanding the cosmos. If Hubble gave us front-row seats to the cosmic magic show, then the James Webb Space Telescope is the backstage pass, allowing us to see how every single trick is engineered from the ground up. Launched on Christmas Day 2021, jwst is not merely an upgrade. It represents a fundamental shift in our ability to perceive the universe. Its primary mission is to act as an infrared telescope, a design choice that is absolutely critical for its role as the ultimate cosmic illusion buster. As light travels across the vast, expanding universe from the most distant objects, its wavelength is stretched by the expansion of space itself. This effect, known as cosmological redshift, shifts the light from the ultraviolet and optical parts of the spectrum into the infrared. For the very first galaxies that formed after the Big Bang, their light has been traveling for over 13 billion years, and by the time it reaches us, it is almost entirely in the infrared. Hubble, designed primarily for optical and ultraviolet light, could only glimpse the faintest reddened hints of these ancient objects. jwst, however, is built to see them in their full glory, pulling back the curtain on the earliest acts of cosmic history. This incredible sensitivity to infrared light is what allows jwst to push gravitational lensing to its absolute limits. Remember, gravitational lensing is often a game of magnification, using the gravity of a foreground galaxy cluster to amplify the faint light from an object far behind it. Hubble used this technique to spectacular effect, but it was often magnifying objects that were already near the edge of its detection capabilities. jwst's larger mirror and sophisticated instruments take this concept to a whole new level. It can see the lensed images of galaxies so distant and faint that they are essentially invisible to any other observatory. We are not just talking about seeing more of the same. We are talking about discovering entirely new classes of objects that have been hidden from view since the dawn of time. These aren't just deeper illusions, they are the primordial deceptions, the first light-bending events that occurred when the universe was in its infancy. The scientific payoff of this enhanced vision is staggering. One of the most pressing questions in cosmology concerns the nature of the very first stars and galaxies, known as population 3 stars. Theorized to be monstrously large, hot, and composed only of hydrogen and helium, these first furnaces forged the first heavy elements and began the process of lighting up the dark, early universe. But they have never been directly observed. jwst, by combining its infrared power with the natural magnification of gravitational lenses, is uniquely positioned to finally spot them. By finding these lensed, magnified images of the first galaxies, astronomers can analyze their light to determine their composition, their temperature, and the processes that govern their formation. This is like using the gravity of a cosmic lens as a time machine to directly observe the universe's first chapter. Furthermore, jwst's ability to take detailed spectra of these lensed objects transforms them from mere pictures into rich sources of physical data. When the light from a distant galaxy is lensed, every single bit of information in that light is amplified, including the subtle, fingerprint-like absorption and emission lines in its spectrum. With jwst, scientists can now obtain exquisitely detailed spectra of galaxies that are far too faint for such detailed study without the lensing boost. These spectra reveal not just what these galaxies are made of, but also their internal motions, the velocity of their gas clouds, and the rate at which they are forming stars. It allows us to perform a remote cosmic autopsy, understanding the life cycle of galaxies billions of years ago with a precision that was previously reserved only for our cosmic neighborhood. This new depth of observation also provides a powerful new tool for investigating the two greatest cosmic mysteries, dark matter and dark energy. The detailed properties of gravitational lenses, the exact sharpness of the Einstein rings, the precise brightness ratios of multiple images, are exquisitely sensitive to the distribution of dark matter within the lensing galaxy cluster. jwst's razor-sharp images allow scientists to map this distribution with unprecedented fidelity, testing different models of what dark matter particles might be like. Is it cold and slow-moving or warm and more energetic? The way it clumps on the smallest scales revealed by these ultra-precise lensing maps will help provide the answer. Simultaneously, by discovering and measuring strong gravitational lensing events at unprecedented distances, jwst provides new data to constrain the properties of dark energy. The rate at which these lenses appear at different cosmic epochs tells us about how the growth of structure in the universe has changed over time, which is directly influenced by the repulsive force of dark energy. Each new lensed galaxy discovered by jwst is another data point in the grand cosmic equation, helping us understand why the expansion of the universe is accelerating. The James Webb Space Telescope is more than just a new set of eyes on the sky. It is the ultimate decoder ring for the universe's most profound illusions, promising to reveal not just how space tricks us, but why. But how do we move from a breathtaking Hubble image of an Einstein ring to a precise measurement of a dark matter halo's mass? How can we be sure that a faint, warped arc in a deep field image is truly a lensed galaxy and not just a strangely shaped object? This is where the real detective work begins, not at the telescope, but inside the immense processing power of supercomputers. To truly decipher the universe's illusions, astronomers have built vast digital universes of their own, complex computer simulations that act as virtual laboratories for testing every possible trick of the light. These aren't simple video game renditions. They are sophisticated mathematical models that encode the known laws of physics, particularly Einstein's general relativity, to predict exactly how light should behave as it journeys through a warped cosmos. Before an astronomer even submits a proposal for telescope time, they can run thousands of these simulations to predict what a specific type of lensing event might look like, essentially allowing them to practice reading the cosmic mirage before they ever see the real thing. The foundation of any gravitational lensing simulation is a realistic model of the lens itself. This starts with the invisible architecture of dark matter. Cosmologists use our best understanding of how dark matter behaves, that it's cold and clumps together under gravity, to generate massive, three-dimensional maps of its distribution throughout the universe. Into this invisible scaffolding, they then sprinkle realistic galaxies and galaxy clusters, governed by the rules of how gas cools, stars form, and black holes grow. The result is a synthetic universe that evolves over billions of virtual years, complete with the same cosmic web of filaments, voids, and massive clusters we observe in the real one. This synthetic cosmos becomes the testing ground. Scientists can choose any point in this digital universe as their virtual Earth, and then command the computer to calculate the path of every single ray of light traveling from a distant background source, through the complex gravitational fields of all the intervening dark matter and galaxies, and finally into their simulated telescope. The magic happens when they compare these simulated images to the actual photos captured by Hubble or Webb. It's a process of exquisite fine-tuning. An initial simulation might produce a warped arc that's too sharp, or an Einstein ring that's too large compared to the real observation. This discrepancy is not a failure, it's invaluable data. It tells the scientists that their initial assumptions about the mass distribution in the foreground lens were slightly off. Perhaps the dark matter halo is more spread out, or maybe it has a different, more complex shape. They then adjust the parameters of their model, the amount of mass, its concentration, the ratio of dark matter to visible matter, and run the simulation again. They iterate this process thousands, even millions of times, using advanced algorithms that automatically learn from each comparison, slowly homing in on the one unique model that perfectly reproduces the observed illusion. In this way, the mirage itself becomes a precise scale. The final, successful simulation doesn't just show a pretty picture. It contains the exact answer to how much mass is in that lensing cluster and exactly how that mass is distributed, right down to the finest details of the invisible dark matter. This computational power is also our primary tool for weeding out false positives. The universe is a vast and random place, and sometimes a faint, odd-shaped galaxy might just happen to lie near a foreground galaxy by pure chance, creating a coincidence that looks deceptively like a weak lensing event. Simulations help quantify the odds of such a chance alignment. By generating millions of mock skies where galaxies are randomly placed, astronomers can calculate how often such deceptive patterns occur naturally. This provides a crucial statistical threshold. If a suspected lensing event is rarer than, say, 1 in a million random simulations, then they can be confident it's the real deal. This process turns the hunt for cosmic mirages from an art into a rigorous science, ensuring that every claimed discovery is backed by solid statistical evidence. These digital universes are more than just predictive tools. They are the essential translators, turning the beautiful but bewildering language of bent light into the hard numbers and precise maps that define our modern understanding of the cosmos. But if we pull our focus from the vast gravitational warping of galaxies and turn our gaze inward to the subatomic realm, we find that the universe's capacity for illusion runs even deeper. Here, in the domain of quantum mechanics, the very concepts of what is real and what is possible are not just bent, they are completely rewritten. This isn't about light being tricked by gravity. This is about the fundamental nature of existence itself engaging in a constant, bewildering magic act. At the quantum scale, particles do not behave like tiny billiard balls. They exist in a haze of probability, defined by waves of potential rather than fixed locations. They can be in multiple places at once, a phenomenon known as superposition, only settling into a definite state the moment we attempt to measure them. This act of observation itself becomes a form of creation, collapsing infinite possibilities into a single reality, suggesting that the very act of looking might shape what we see in the most profound way imaginable. Consider one of the most startling quantum illusions, the spontaneous appearance of virtual particles. According to the laws of quantum physics, empty space is not truly empty. It is a seething, bubbling foam where pairs of particles and antiparticles constantly flicker into existence out of pure energy, only to annihilate each other and vanish back into the void an instant later. This isn't just theoretical. We can measure the effects of this quantum frenzy. It's responsible for a small but measurable shift in the energy levels of atoms, known as the Lamb shift, and it even creates a faint force, the Casimir effect, where two metal plates placed incredibly close together in a vacuum are gently pushed together by the pressure of these virtual particles popping off outside them. This means that what we perceive as true, empty vacuum is in fact a cauldron of spontaneous creation and destruction, a foundational level of reality that is utterly hidden from our direct perception, yet has measurable consequences for the world we do see. Then there is the phenomenon of quantum entanglement, which Einstein himself famously derided as spooky action at a distance. When two particles become entangled, they lose their individual identities and become linked into a single, unified quantum system. No matter how far apart you separate them, across a lab or across the galaxy, measuring the state of one particle will instantly determine the state of the other. This connection seems to operate faster than the speed of light, challenging our most basic understanding of cause, effect, and the nature of information. It creates a universe where things are connected in ways that defy classical logic, suggesting a deeply interwoven fabric of reality where separation itself might be the ultimate illusion. While this doesn't create a visual mirage we can photograph, it represents a profound deception of locality, hinting that the universe might be fundamentally non-local at its core. The greatest puzzle lies at the intersection of these two revolutionary theories, quantum mechanics and general relativity. General relativity gives us a magnificent picture of gravity as the smooth, geometric curvature of spacetime, a theory that works flawlessly on the scale of planets, stars, and galaxies. Quantum mechanics gives us an equally powerful picture of the probabilistic, fuzzy world of particles and forces. The problem is, these two titans of physics are fundamentally incompatible. They speak different mathematical languages and make contradictory claims about the nature of reality. This conflict becomes most apparent in the heart of a black hole or at the moment of the Big Bang, where densities and energies are so immense that the quantum nature of gravity itself must become important. We currently have no complete theory of quantum gravity to describe what happens in these extreme environments. Some of the most promising candidates, like string theory or loop quantum gravity, propose breathtakingly strange ideas that spacetime itself might be emergent from something more fundamental, perhaps woven from countless entangled quantum bits, or that the universe has more than the three spatial dimensions we experience. This quest for a unified theory suggests that the very stage upon which cosmic mirages like gravitational lensing play out the four-dimensional fabric of spacetime might itself be a kind of illusion, a smooth, classical approximation of a reality that is ultimately granular and probabilistic. The warping of light by a galaxy cluster would then be a large-scale consequence of untold trillions of quantum interactions happening at the Planck scale. Exploring this frontier reminds us that the deception is not limited to what we see through our telescopes. It is woven into the very laws that govern existence, from the smallest quanta to the largest clusters of galaxies. The quantum realm hints that the universe is not just stranger than we imagine. It is likely stranger than we can imagine, presenting a reality where our classical intuitions are not just occasionally fooled, but are fundamentally inadequate to describe the true, wondrously weird nature of things. We've seen how the immense gravity of a black hole or a galaxy cluster can bend the path of light, creating spectacular visual deceptions across the cosmos. But what if the universe's greatest trick isn't something you can see at all, but something you experience? What if gravity's power extends beyond warping space to actually warping time itself? This isn't science fiction. It's a fundamental prediction of Einstein's general relativity known as time dilation, a phenomenon that reveals time is not the universal, constant metronome we perceive it to be. Instead, it's a fluid, personal experience, intimately woven into the very fabric of spacetime and directly influenced by the gravitational fields we find ourselves in. The core idea is both simple and utterly mind-bending. The stronger the gravity, the slower time flows. Imagine two identical, incredibly precise atomic clocks, both synchronized to tick in perfect unison. Now place one clock at sea level here on Earth and carry the other to the top of a tall mountain, where the gravitational pull is ever so slightly weaker. Leave them there for a while. When you bring the mountain clock back down and compare them, you would find a measurable difference. The clock that spent time in the stronger gravitational field at sea level will have ticked fewer times than the clock on the mountain. It will have literally experienced less time. The difference is tiny, a matter of nanoseconds over a year, but it is real and has been confirmed by countless experiments. This means that for someone living in a basement, time actually passes a tiny bit more slowly than for their neighbor in a penthouse apartment. You are literally aging slower the closer you are to a source of gravity. This temporal trickery is not limited to our planet's subtle pull. The effect becomes exponentially more dramatic near immensely massive objects. Picture a hypothetical spacecraft on a mission to observe a black hole from a safe distance. If they were to send a probe on a closer approach, something truly bizarre would happen from the perspective of the main ship. As the probe descended into the black hole's intense gravity well, its signals would begin to slow down. The intervals between each pulse would get longer and longer. The probe itself wouldn't notice anything amiss. From its point of view, its clock would be ticking normally. But to the astronauts watching from afar, the probe would appear to be moving in extreme slow motion, its signals becoming drawn out and red-shifted until they finally fade away entirely as it crosses the event horizon. The probe hasn't just looked like it slowed down. From the perspective of the outside universe, its entire timeline has been stretched out. It has experienced a profound form of temporal distortion. We don't have to venture to a black hole to prove this happens. Our daily lives are utterly dependent on this correction. The Global Positioning System, or GPS, is a perfect example of practical, applied relativity. The network of satellites orbiting Earth are in a weaker gravitational field than we are on the surface, and they are also moving at high speed, which causes a separate velocity-based time dilation effect. If the incredibly precise atomic clocks on these satellites weren't constantly corrected for both general and special relativity, the entire system would fail within minutes. The timing errors would accumulate, making your phone's map navigation increasingly inaccurate by several miles each day. Engineers must deliberately program the satellite clocks to tick at a slightly different rate before launch so that once they are in orbit, their perception of time synchronizes with ours on the ground. Our ability to navigate relies entirely on our understanding that time is relative. This concept shatters the Newtonian idea of a single, universal clock ticking away in the background of the universe. There is no now that applies everywhere. Your now is personal to you and your specific location in spacetime's gravitational landscape. This temporal deception is perhaps the most profound of all the cosmos's tricks because it is so personal. It directly alters our experience of reality, not as a visual illusion we can observe from a distance, but as a fundamental aspect of our existence. It tells us that space and time are not separate entities, but are inextricably linked as a single, malleable continuum spacetime that can be curved by mass and energy. Where gravitational lensing shows us that we cannot always trust our eyes, time dilation shows us that we cannot even fully trust the steady, reliable tick of a clock. The universe doesn't just fool our vision, it rewrites the very rules of time itself for every single object within it. So if time itself is a flexible experience and the quantum realm suggests a foundation of probability, where does that leave our perception of a single, objective cosmos? This line of questioning pushes us toward one of the most speculative yet captivating ideas in modern cosmology, the multiverse theory. This concept proposes that our entire universe, with its hundreds of billions of galaxies and its seemingly endless expanse, might not be the entirety of existence. Instead, it could be just one bubble in a vast, frothing cosmic foam of universes, each with its own unique set of physical laws, constants, and perhaps even dimensions. In such a framework, the very idea of a true reality becomes profoundly relative. What we perceive as the fundamental and unchangeable rules of our existence, the strength of gravity, the mass of an electron, the very speed of light, might be nothing more than the local bylaws of our particular cosmic neighborhood, utterly different in the universe next door. This radical idea emerges naturally from several well-respected, though unproven, theoretical models. The most prominent is eternal inflation, a theory that extends our understanding of the Big Bang. It suggests that the rapid inflationary expansion that jump-started our universe never truly stopped everywhere. Instead, it continues eternally in a broader background space. But within this inflating energy field, random quantum fluctuations cause pockets to stop inflating and instead crystallize into stable universes with random physical properties. Our universe would be one such pocket, Another path to the multiverse comes from string theory, which requires extra spatial dimensions beyond the three we experience. The mathematics of string theory allows for a staggering number of possible stable configurations for these extra dimensions, perhaps 10 to the 500 different ways. Each configuration would manifest as a universe with a different set of physical laws and constants. In this string landscape, our universe is simply one possible solution that actually manifested, with the right delicate balance to allow for galaxies, planets, and life. But how could we ever detect another universe if, by definition, it exists in a domain completely separate from our own spacetime? This is where the line between established physics and speculative thought experiments becomes fascinatingly blurred. Some theorists have pondered whether a truly colossal gravitational lensing event, perhaps involving a universe-scale mass, could create a distortion so extreme that it might briefly reveal a signature of a neighboring cosmos. Others have considered the possibility of a direct, violent collision between two expanding bubbles in the multiverse foam. Such a collision would leave an imprint on the cosmic microwave background, the leftover radiation from the Big Bang, in the form of a distinct circular pattern of temperature variations. Scientists have actively searched for such an imprint, and while a few tentative and controversial anomalies have been proposed, no conclusive evidence has ever been found. For now, these ideas remain in the realm of tantalizing possibility, pushing the limits of what is observable and testable. The philosophical implications of the multiverse are perhaps even more staggering than the scientific ones. It forces us to confront the anthropic principle, the idea that the fundamental constants of our universe seem finely tuned to allow for the existence of life. If there is only one universe, this apparent fine-tuning seems like an incredible, almost miraculous coincidence. But if there are an infinite number of universes, each with random constants, then it's no surprise that we find ourselves in one of the rare ones where the numbers worked out right for life to emerge. We are not witnessing a miracle, we are simply the beneficiaries of a cosmic lottery with an immense number of losing tickets. This perspective doesn't diminish our universe's wonder, it simply reframes it, suggesting that our reality is not necessarily special or central, but simply possible. Ultimately, the multiverse theory represents the final, most expansive form of cosmic mirage. It proposes that the entire stage upon which all other illusions play out, our universe itself, might be part of a grander deception. It challenges the bedrock assumption that there is one objective reality to be perceived, suggesting instead that what we call reality is merely our local perspective, a single view from one bubble in an unfathomably vast metaphysical ocean. While it remains firmly in the domain of theoretical speculation, it completes a profound arc of thought, from light being bent by galaxies, to time being warped by gravity, to the quantum realm defying classical logic, and finally to the possibility that our entire cosmic home is just one illusion in an endless hall of mirrors. It invites us to consider that the greatest trick the cosmos plays is convincing us it is the only one. Long before the first telescope was ever pointed skyward, humanity was already grappling with the cosmos's capacity for illusion, weaving intricate stories to explain the bewildering sights unfolding above. Our ancestors looked up and saw not a cold, mechanistic void, but a vibrant, living tapestry where gods, spirits, and heroes played out dramas that directly influenced their lives. A sudden, unexpected eclipse wasn't a predictable orbital alignment. It was a dragon or a demon devouring the sun, a terrifying omen of a king's death or a coming famine that demanded drums be beaten and arrows shot into the sky to frighten the beast away. The unpredictable appearance of a comet with its long, ethereal tail was never a good sign. It was a celestial messenger of doom, a fiery sword heralding invasion, plague, or the fall of an empire. Its path across the constellations carefully charted by terrified court astrologers. Even the more predictable movements of the planets were seen as deceptive tricks. The planet Mercury, for instance, was notoriously difficult to track because it never strays far from the sun's glare. To the ancient Greeks, this elusive behavior perfectly embodied the god Hermes, the swift-footed trickster and patron of thieves, who moved in and out of view as if playing a cunning game of celestial hide and seek. These mythologies were far more than just primitive superstition. They were the foundational framework of early science, representing humanity's first brave attempt to impose order on a chaotic and often frightening universe. By attributing these events to the whims of conscious beings, gods who could be angered, appeased, or understood, people created a world that was intelligible. The sky became a storybook, and every strange event was a new paragraph in an ongoing narrative about the relationship between the divine and the mortal. The Norse people saw the shimmering, dancing curtains of the aurora borealis as the armor of the Valkyries, warrior women who chose which heroes would die in battle and be taken to Valhalla. The Aboriginal peoples of Australia looked at the dark patches within the Milky Way not as clouds of obscuring dust, but as the silhouette of a great emu in the sky, a creator spirit whose position told them when to gather eggs. These interpretations provided not just an explanation, but meaning, purpose, and a profound connection to the cosmos. They were a way of asserting that we were not separate from the universe, but active participants in its grand, unfolding story. The shift from this mythological understanding to a scientific one was not merely a change of explanation, but a revolution in perception. It required a fundamental reimagining of our place in the cosmos. The work of pioneers like Galileo, who turned his telescope on Jupiter and saw its moons orbiting a center other than Earth, began to dismantle the idea of a universe centered around us. It showed that the heavens were not a perfect, unchanging realm of deities, but a physical place that could be observed, measured, and understood through mathematics and reason. The cosmic mirages were no longer the tricks of capricious gods. They were the lawful, predictable consequences of gravity and light. An eclipse became a breathtaking celestial coincidence of size and distance, not a supernatural omen. A comet transformed from a portent of disaster into a frozen relic from the solar system's formation, a dirty snowball following a precise elliptical path dictated by gravity. Yet, for all the power and clarity that science has brought, the ancient allure of the cosmic trick has never truly faded. That primal sense of wonder, that feeling of awe when confronted with a sky that doesn't behave as expected, is something that still connects us directly to our ancestors. When we look at a Hubble image of an Einstein ring, we are not so different from the ancient stargazer who saw a face in the moon. We are still pattern-seeking creatures, driven by a deep and timeless curiosity to decode the mysteries presented to us. The language we use has changed from myth to mathematics, from storytelling to computer simulation, but the essential urge remains identical: to peel back the layers of deception and see the universe for what it truly is. Our modern tools have simply given us a more powerful lens, allowing us to appreciate the true scale and sophistication of the cosmos's illusions, revealing that the reality behind the myth is infinitely more strange and magnificent than any story ever told. But the greatest leaps will likely come from entirely new ways of listening to the cosmos. While we marvel at the visual distortions of light, space-based gravitational wave observatories are being designed to hear an entirely different kind of cosmic mirage. Projects like the Laser Interferometer Space Antenna, or LISA, envision a trio of spacecraft flying in a precise triangular formation millions of kilometers apart, connected by lasers. This colossal instrument will be sensitive to the low-frequency ripples in spacetime generated by the mergers of supermassive black holes at the hearts of distant galaxies. These waves don't create a visual distortion, but they represent a profound warping of reality itself. As they pass through matter, they minutely stretch and compress the fabric of space, and in doing so, they could potentially create fleeting, secondary lensing effects on any light traveling through the disturbed region. Detecting this would open an entirely new window on gravity's trickery, allowing us to observe how the universe's most violent events can momentarily rewrite the rules of perception across unimaginable distances. This explosion of new data will demand a revolution in how we process and understand it. The Vera C. Rubin Observatory alone is expected to generate over 20 terabytes of data every single night, an avalanche of information so vast that no single human could ever hope to sift through it. This is where the next frontier truly lies, at the intersection of astronomy, physics, and advanced data science. The future of cosmic mirage research will be driven by increasingly sophisticated artificial intelligence and machine learning algorithms. These systems are already being trained to perform the Herculean task of finding the subtle, telltale distortions of weak gravitational lensing among billions of perfectly normal galaxies, a feat akin to identifying a single unique grain of sand on every beach on Earth. These AIs don't just find the needles in the haystack, they are beginning to help us understand the haystack itself, running complex simulations in reverse to decode the exact distribution of dark matter that must be present to create the patterns of bent light we observe. This interdisciplinary fusion will transform these illusions from curious anomalies into precise quantitative tools, turning the universe's deceptions into our most reliable guides. What does this all mean for our understanding of reality? Each new lensing event is a natural experiment, a chance to test the laws of physics in environments we could never hope to recreate in a lab. As we gather millions of these experiments, we will be able to probe the very nature of gravity itself. Does Einstein's theory of general relativity hold perfectly true across the entire history of the universe? Or will we begin to see subtle deviations that point toward a new, more complete theory? The precise shapes of Einstein rings and the statistics of distorted galaxies could reveal the answer. Furthermore, by combining the data from optical lensing surveys with the new auditory sense provided by gravitational wave astronomy, we will achieve a multi-messenger, multi-dimensional view of cosmic deception. We will be able to see the dark matter and hear the ripples it creates, building a holistic picture of a universe that is infinitely more dynamic and interconnected than we ever imagined. The future promises not just a catalog of stunning illusions, but a deeper, more nuanced conversation with the cosmos, one where we finally learn to speak the language of its most elegant tricks. Imagine trying to explain to a classroom of students that an invisible substance called dark matter makes up most of the universe's mass, or that gravity can bend the path of light itself. These are not easy concepts to grasp from a textbook alone, but show them a photograph from the Hubble Space Telescope of a perfect Einstein ring, a glowing halo of light from a distant galaxy warped around a foreground cluster, and suddenly the abstract becomes tangible. That image is not just a pretty picture, it is a direct visual testament to the warping of spacetime, a story told in starlight that makes the incredible real. This is the unparalleled educational power of cosmic mirages. They transform the most daunting pillars of modern physics from dry equations on a page into breathtaking celestial events that students can see and wonder about, creating a gateway to curiosity that is both immediate and profound. The magic lies in their ability to demonstrate complex principles through clear, visual storytelling. General relativity, for instance, is famously counterintuitive. The idea that mass curves the fabric of space-time and that this curvature guides the motion of everything within it is a radical departure from our everyday experience of forces. You can talk about rubber sheets and bowling balls as an analogy, but that only goes so far. A gravitational lensing event like the Einstein cross does the explaining for you. Here, a single quasar appears as 4 distinct images arranged in a perfect symmetry around a central galaxy. The visual is so striking and so seemingly impossible that it demands an explanation. It forces the question, how? And in answering that question, students are led directly to Einstein's revolutionary idea. They aren't just learning about relativity, they are seeing its most dramatic prediction confirmed in a single, unforgettable snapshot. The cosmic mirage becomes the ultimate teaching assistant, making the complex not just comprehensible, but visually undeniable. This approach to learning extends far beyond the classroom wall, creating powerful and accessible entry points for public science engagement. Planetarium shows and science center exhibits can use immersive visualizations to fly audiences through a simulated universe, allowing them to witness first and how light bends around a black hole or how a dark matter halo distorts the images of background galaxies. Virtual reality experiences can take this a step further, letting users manipulate the mass of a virtual galaxy cluster and watch in real time as the gravitational lensing effects strengthen or weaken. This hands-on, interactive exploration transforms passive observers into active participants in the process of discovery. They are no longer just being told that dark matter exists. They are effectively measuring its influence themselves by observing how it bends light, internalizing the scientific method through direct experience. It demystifies the process of science, showing that it is fundamentally about observing effects and deducing their causes. For educators, these cosmic phenomena provide a rich toolkit for activities that cost little to nothing but yield enormous engagement. A simple but powerful demonstration involves using a wine glass. The curved bottom of the glass can act as a gravitational lens when placed over a printed pattern or a grid of lines, stretching and distorting the image beneath it in a way that perfectly mimics how a galaxy cluster bends the light from objects behind it. Students can immediately draw the parallel. The glass is the gravitational lens, and the distorted lines are the background galaxies. This simple model makes an abstract concept instantly graspable. More advanced projects might involve using free online software that allows students to input different mass distributions for a simulated galaxy, and then calculate and visualize the resulting lensing patterns, bringing a taste of real cosmological research into the classroom. Ultimately, the greatest lesson cosmic mirages teach is the very nature of scientific inquiry itself. They are the perfect embodiment of the idea that things are not always as they appear, and that truth often requires peeling back layers of perception. A strange, arc-shaped object in a telescope image isn't accepted at face value. It is investigated, modeled, and ultimately revealed to be a trick of the light caused by invisible matter. This process fosters a crucial scientific mindset, healthy skepticism, and rigorous critical thinking. It shows students that science isn't a static set of facts to be memorized, but a dynamic process of questioning, testing, and revising our understanding of the world. By starting with a beautiful illusion, educators can guide learners to a much deeper appreciation for the painstaking, creative, and awe-inspiring work of uncovering reality's secrets, proving that the universe's most captivating tricks are also its most valuable teachers. But as we hand over more of the analytical heavy lifting to artificial intelligence, a new set of challenges emerges. ones that are less about the laws of physics and more about the principles of responsible science. The process of identifying a gravitational lens in a vast sea of telescopic data is no longer a task for the human eye alone. It requires sophisticated algorithms trained to recognize the subtle warping of distant galaxies, a digital sieve that can process millions of images in the time it takes an astronomer to review a handful. The ethical imperative here is one of algorithmic transparency. We must ask, what exactly is the machine learning model looking for? If the training data used to teach the AI is itself biased, for instance, if it contains only the most dramatic and obvious examples of strong lensing, then the algorithm may develop a blind spot, systematically overlooking the fainter, more subtle distortions that are just as scientifically valuable. This isn't a hypothetical glitch. It's a form of embedded prejudice that could skew our entire census of cosmic mirages, leading us to believe these events are rarer or occur in only certain types of environments, thereby distorting our maps of dark matter before we even begin. The consequences of such a misinterpretation ripple far beyond a single incorrect data point. Our cosmological models are intricate, interlocking webs of theory and observation. A flawed measurement of the distribution of dark matter, inferred from biased lensing data, could lead to an incorrect calculation of the universe's expansion rate, fueling the ongoing tension surrounding the Hubble constant. This isn't just an academic disagreement. It strikes at the heart of our understanding of the cosmos's origin, evolution, and ultimate fate. If the foundation of our data is compromised by unseen algorithmic bias, the entire theoretical structure built upon it becomes unstable. The ethical duty, therefore, extends to rigorous and continuous validation. Researchers have a responsibility to constantly interrogate their digital tools, to run controlled simulations where the answer is known, and to ensure their AI is not just finding patterns, but finding the right patterns for the right reasons. It demands a culture of openness where the code behind these discoveries is made available for scrutiny, allowing the wider scientific community to audit the methods and verify that the conclusions are driven by the cosmos, not by a flaw in the programming. This commitment to clarity becomes even more critical when these profound discoveries are translated for the public. The moment a press release is drafted about a new, strange cosmic mirage, an ethical tightrope must be walked. There is a powerful temptation to sensationalize, to use language like mystery solved or physics broken to capture headlines. But such framing can create a damaging cycle of hype and disappointment, eroding public trust in science when the initial, exciting interpretation is later refined by more careful study. The responsible path is to communicate with both wonder and integrity, clearly distinguishing between what is solidly observed, what is a likely interpretation, and what remains an open question. It means avoiding the trap of anthropomorphism, like saying a black hole feeds or a galaxy collides, without also explaining these are metaphorical shortcuts for complex physical processes. The goal is to invite the public into the authentic, often messy process of scientific discovery, not to present it as a series of flawless, earth-shattering proclamations. Ultimately, the study of cosmic illusions holds up a mirror to our own practices. It reminds us that our view of the universe is always mediated, first by the laws of physics that bend the light, then by the instruments we build to collect it, and finally by the algorithms and human minds we use to interpret it. Each step in this chain introduces its own potential for distortion, its own ethical requirement for vigilance. Ensuring the integrity of this entire pipeline, from the raw photons hitting a telescope's sensor to the headline on a news feed, is what protects the integrity of science itself. It is a profound reminder that the quest to understand the cosmos is not a purely technical endeavor, but a deeply human one, requiring not only intelligence and curiosity, but also humility, transparency, and an unwavering commitment to the truth. There is a profound and often overlooked dialogue between the rigor of scientific discovery and the boundless imagination of artistic expression, and nowhere is this conversation more vivid than in our collective awe for cosmic mirages. When an astronomer studies a Hubble image of an Einstein ring, they see a precise measurement of dark matter, a set of data points to be analyzed and modeled. But when an artist gazes upon that same image, they see something else entirely: a celestial halo, a perfect omen written in starlight, a visual metaphor for the ways our own perceptions can be warped and transformed. This single object, a product of immutable physical law, becomes a muse, sparking creations that explore the deepest questions of what is real and what is illusion. The journey of inspiration flows both ways. The scientist's calculation provides the raw, stunning material, and the artist's interpretation gives it a human heartbeat, allowing the rest of us to feel the emotional weight of the discovery. This cross-pollination has given rise to an entire genre of cosmic art, where painters and digital creators use the visual language of gravitational lensing to craft worlds that feel both alien and strangely familiar. Digital artists might use software to simulate the warping of spacetime around a black hole, not to calculate its mass, but to create a breathtaking backdrop for a narrative scene, a place where the very light curves in a silent, graceful dance. Painters have long been drawn to the nebulous forms of galaxies, but now they incorporate the specific distortions of lensing, stretched arcs, multiple images, radiant halos, to infuse their work with a heightened sense of cosmic wonder and disorientation. These artworks do more than just illustrate a scientific concept. They internalize it and reimagine it through an emotional lens. They ask the viewer not to calculate, but to contemplate, to feel the sheer scale and mystery of a universe that can bend the paths of stars themselves. The influence extends powerfully into the realms of literature and film, where the mind-bending implications of these phenomena provide fertile ground for storytelling. Science fiction authors have woven gravitational lensing and time dilation into the very fabric of their plots for decades. A story might feature a spaceship using a neutron star's immense gravity as a slingshot, with the crew witnessing the entire external universe warp around them in a terrifying and beautiful spectacle. Another narrative could explore the social implications of time dilation, where a team of scientists orbiting a black hole ages only years while centuries pass on Earth, returning to a home that has forgotten them. These are not just cool special effects. They are central to the narrative, forcing characters, and by extension the audience, to confront the fluid and relative nature of reality itself. The cosmic mirage becomes a plot device that challenges the most fundamental aspects of identity, memory, and human connection. This synergy reaches its most immersive form in large-scale installations and digital exhibitions found in planetariums and modern art museums. Here, artists and scientists often collaborate directly, using high-resolution data from telescopes to create room-sized experiences. Imagine stepping into a dark room where a projection of a galaxy cluster is mapped across the walls and ceiling. As you walk through the space, your movement triggers simulations of gravitational lensing, causing the background galaxies to stretch and swirl around you in real time. You are no longer a passive observer. You are inside the mirage, physically engaging with the distortion of space. These projects dissolve the boundary between observer and phenomenon, making an abstract, astronomical concept a visceral, personal experience. They exemplify how art can function as a unique form of science communication, translating complex data into a language of light, sound, and emotion that resonates on a primal level. Ultimately, this flourishing of creativity around cosmic illusions speaks to a universal human need. We are pattern-seeking storytellers, and the universe, in its most magnificent deceptions, provides the ultimate source material. The artist does not seek to compete with the scientist for an explanation, but to complement it with a reflection. Where science gives us the equations for how light bends, art explores what it feels like to have your reality bent. It gives form to the awe, the humility, and the sublime curiosity that these discoveries evoke. This cultural response confirms that these mirages are more than just astronomical phenomena. They are profound cultural touchstones. They remind us that our drive to understand the cosmos and our desire to find beauty within it are not separate endeavors, but intertwined expressions of the same enduring human spirit, forever reaching for the stars. It might seem like the study of cosmic mirages is a purely theoretical pursuit, a fascinating but abstract game of understanding how light bends across billions of light years. Yet, the techniques and technologies developed to decode these distant illusions are already finding powerful, practical applications right here on Earth, quietly improving fields from medicine to machine learning. This incredible cross-pollination of ideas demonstrates a beautiful truth. By striving to understand the universe's grandest deceptions, we often develop the tools to see our own world with startling new clarity. The algorithms and optical principles forged in the fires of cosmology are now being repurposed to diagnose disease, guide autonomous vehicles, and push the boundaries of computational vision. Consider the monumental challenge astronomers face when analyzing a gravitational lensing event. A single image from the James Webb Space Telescope might contain thousands of faint background galaxies whose shapes have been subtly distorted by an intervening cloud of dark matter. Disentangling this cosmic signal from the noise requires incredibly sophisticated software algorithms capable of recognizing patterns, reconstructing original shapes from distorted data, and performing statistical analysis on an immense scale. This very same class of problem appears in a dramatically different context: medical imaging. The algorithms originally designed to see through a gravitational mirage and reconstruct the true shape of a distant galaxy are now being adapted to help doctors see through the complexities of the human body. For instance, in magnetic resonance imaging or computed tomography scans, the raw data collected by the machine is often a distorted representation of the underlying tissue. By applying techniques similar to those used in weak lensing analysis, researchers can develop new image processing tools that dramatically enhance the clarity of these scans, allowing for the earlier and more accurate detection of tumors, neurological disorders, and other conditions. The mathematics developed to map the invisible dark matter of the cosmos is now helping to illuminate the hidden structures within us. The influence of this cosmic research extends even further into the realm of artificial intelligence. Training a machine learning system to identify a genuine gravitational lens among millions of galaxy images is a classic exercise in pattern recognition. Astronomers have fed vast datasets, both real observations and complex simulations, into neural networks, teaching them to spot the telltale signs of warped and stretched galaxies with superhuman speed and accuracy. This rigorous training has directly advanced the entire field of computer vision. The convolutional neural networks honed on cosmic data are now being deployed in security systems for facial recognition, in agricultural technology to monitor crop health from drone footage, and perhaps most importantly, in the development of perception systems for self-driving cars. These vehicles must instantly interpret a chaotic visual landscape, distinguishing a pedestrian from a lamppost, a plastic bag blowing across the road from a running animal. The ability to quickly and accurately reconstruct a scene from partial or distorted visual information is paramount, and it's a skill that AI first learned in many ways by studying the deepest tricks of the cosmos. Beyond software, the pure physics of gravitational lensing is inspiring innovation in materials science and optical engineering. The way gravity bends light around a massive object is, in essence, a natural demonstration of a perfect lens, one far more powerful than any glass we can grind on Earth. While we can't recreate a black hole's gravity well in a lab, scientists are exploring the creation of metamaterials, artificial substances engineered to have optical properties not found in nature. These metamaterials can be designed to bend electromagnetic waves, including visible light, radio waves, or microwaves, in precise and unusual ways, a concept known as transformation optics. The mathematical framework used to describe how space-time curves around a mass is directly applicable to designing these materials to curve light in a controlled manner. This research could one day lead to the development of superlenses capable of viewing objects smaller than the wavelength of light, revolutionizing microscopy, or to advanced cloaking technologies that guide light around an object, rendering it effectively invisible. The ultimate inspiration for such science fiction, like advancements, comes from the very real and very well understood principles of general relativity that first explained why starlight bends around the sun. The universe's greatest tricks are not just for our wonder, they are a blueprint for the next generation of technological marvels, proving that the pursuit of fundamental knowledge often lights the path to the most practical and transformative innovations. Even with the most powerful telescopes ever built, the quest to capture and decipher the universe's grandest illusions is a constant battle against a host of earthly and cosmic adversaries. Our own atmosphere, that thin layer of gas that makes life possible, is the first and most persistent foe. While it protects us, it also acts like a constantly shifting lens, its turbulent pockets of warm and cool air bending starlight in random ways. This is what causes the familiar twinkle of the stars, a beautiful but scientifically frustrating phenomenon known as astronomical scintillation. For an astronomer trying to measure the minuscule, coherent distortion of a weak gravitational lensing event, this atmospheric jitter is like trying to detect the subtle ripples from a pebble dropped in a pond during a hurricane. The delicate signal from a dark matter filament, which might be stretching 1,000 distant galaxies by just 1%, is completely drowned out by this visual noise. This is the primary reason we launch telescopes like Hubble and Webb into space, not just to get closer to the stars, but to get above the blurring veil of our own air, to a vantage point where the cosmos comes into truly sharp focus. But escaping the atmosphere is only the first hurdle. The instruments we build have their own limitations that can create deceptive artifacts or hide the very signals we seek. Every telescope is a complex machine with mirrors, supports, and detectors, and each component can introduce its own form of illusion. The bright spikes emanating from stars in so many astronomical images, for instance, are not real features of those stars. They are diffraction spikes caused by the thin supports that hold a telescope's secondary mirror in place. While often aesthetically pleasing, these spikes can sometimes obscure faint, lensed galaxies lying close to a bright foreground star. Furthermore, the digital sensors that capture the light, known as charge-coupled devices or CCDs, are not perfect. They can have tiny defects or hot pixels that mimic the appearance of a distant point source, distinguishing a genuine microlensing event, a single star briefly flaring in brightness due to an invisible planet, from a random sensor glitch requires painstaking verification through multiple observations and independent telescopes. The tools we create to reveal the truth are themselves capable of generating their own convincing lies, demanding a rigorous process of calibration and cross-checking. Perhaps the most daunting challenge is the sheer faintness of the signals involved. To detect the weak gravitational lensing caused by the cosmic web of dark matter, astronomers must collect the light from thousands of the most distant, dim galaxies. This isn't a quick snapshot. It requires incredibly long exposure times, often totaling dozens or even hundreds of hours focused on a single patch of sky. The Vera C. Rubin Observatory, poised to begin its legacy survey of space and time, will dedicate years to this very task. During these marathon observations, other transient events can masquerade as lensing. A passing asteroid within our own solar system might streak through the frame, leaving a trail that could be mistaken for a lensed arc. The flickering of a variable star or the sudden flare of a distant supernova can inject false signals into the data. Is that faint, smudged object a galaxy stretched by dark matter? Or is it two unrelated galaxies that just happen to lie close together along our line of sight by pure random chance? Teasing apart the true mirages from the false alarms is a statistical nightmare, requiring the analysis of billions of galaxies to find the coherent patterns that betray the hand of gravity. This is where the human element of patience and collaboration becomes as important as the technological one. No single observation is ever taken as conclusive proof. A potential new gravitational lens discovered by one telescope must be confirmed by another, preferably using a different wavelength of light or a different imaging technique. The data then undergoes a gauntlet of computer modeling, where teams of researchers run millions of simulations to see if their hypothesized mass distribution can actually produce the observed distortion. It's a slow, iterative process of hypothesis and refinement that can take years from the initial detection to a published, peer-reviewed result. This meticulous perseverance, however, pays dividends far beyond a single discovery. Every challenge overcome in the hunt for cosmic mirages forces innovation. The struggle to correct for atmospheric turbulence led to the development of adaptive optics systems for ground-based telescopes, which now have applications in ophthalmology for capturing razor-sharp images of the human retina. The powerful algorithms created to find faint lensing signals are now improving pattern recognition in medical diagnostics and artificial intelligence. The pursuit of clarity amid the cosmos's greatest deceptions doesn't just reveal the secrets of dark matter and black holes. It sharpens our vision for exploring every corner of the known universe. For centuries, philosophers have wrestled with a fundamental question: is the world we perceive the world as it truly is? Cosmic mirages bring this ancient debate roaring into the modern era, providing not just abstract thought experiments, but concrete, observable evidence that our senses are fundamentally unreliable messengers. We naturally assume that our eyes give us a direct and accurate window onto reality, that a star is where we see it and a galaxy is the shape it appears. But gravitational lensing shatters this naive realism. It demonstrates with stunning clarity that the universe itself is a master editor, manipulating the information that reaches us and presenting a version of events that has been filtered, warped, and rearranged. If the cosmos can so easily craft a convincing illusion on a scale of billions of light years, it forces us to confront a humbling possibility that all of our perceptions, even on Earth, might be a kind of mirage, a user interface constructed by our brains that is useful for survival, but not necessarily a perfect reflection of objective truth. This line of thinking resonates powerfully with philosophical ideas that are centuries old. The 18th century German philosopher Immanuel Kant proposed a distinction between the Noumenon, the world as it exists in itself, independent of our perception, and the phenomenon, the world as it appears to us after being processed by the inherent structures of our minds. He argued that we can never truly know the noumenal world. We are forever trapped experiencing the phenomenal one, a reality shaped by our own cognitive lenses. A gravitational lens is a breathtaking physical manifestation of this Kantian principle. The lensing galaxy acts as the ultimate cognitive filter. It takes the noumenal reality of the distant quasar and processes it through the distorting geometry of its gravity, delivering to us a phenomenal appearance, the Einstein cross, that is real in its effect but utterly different from the thing in itself. The universe, it seems, is not just governed by physical laws but also by philosophical ones. In our current technological age, this skepticism finds a new expression in the simulation hypothesis, the idea that our entire reality might be an elaborate construct, a hyper-advanced simulation running on some unfathomable computer. Proponents of this theory often point to the very same quantum weirdness and cosmic mysteries we've explored as potential evidence. They ask if the universe can be described with mathematical precision, and if its fundamental components behave like discrete bits of information, could that be because it is a computation? When we observe the universe performing what looks like a rendering trick like gravitational lensing, where distant objects are computationally duplicated to save processing power, it can feel eerily like glimpsing the code beneath the graphics. While this remains a highly speculative and ultimately untestable idea for now, its cultural traction reveals a deep-seated human intuition, awakened by modern cosmology, that reality is not as solid and self-evident as it seems. Ultimately, the greatest lesson from these cosmic deceptions is one of profound humility. Every time an astronomer uses a supercomputer to reverse engineer a gravitational lens, to subtract the distortion and glimpse the true galaxy behind the mirage, they are performing a philosophical act. They are acknowledging the limits of raw observation and asserting that to find truth, we must first understand the mechanisms of our own deception. This journey from illusion to understanding is the very essence of the scientific endeavor. It applies equally to the distortions of our atmosphere, the biases of our instruments, and the ingrained patterns of our own thought. The cosmos, through its most magnificent tricks, teaches us that the path to knowledge isn't about seeking perfect, unbiased perception, because that may be forever impossible. Instead, it is about learning to read the distortions themselves, to understand the lens so completely that we can see through it. In doing so, we don't just map the dark matter of the universe, we begin to map the boundaries of our own understanding. Imagine having the power to bend light around a black hole or map the invisible hand of dark matter from your own computer. Not long ago, these would have been fantasies reserved for professional astronomers with access to the world's most powerful telescopes. Today, that same sense of discovery is available to anyone with an internet connection, thanks to a revolution in interactive tools and citizen science projects that have flung open the doors of cosmic exploration. This isn't about watching pre-rendered simulations. It's about rolling up your virtual sleeves and diving into the real data, becoming an active participant in the process of scientific discovery. The universe's greatest tricks are no longer just for us to observe. They are for us to experiment with, to manipulate, and to understand through direct, hands-on engagement. At the forefront of this movement are platforms like Zooniverse, a citizen science portal that brings the public into the heart of cutting-edge research. One of its most prolific projects is Galaxy Zoo, which has harnessed the power of hundreds of thousands of volunteer classifiers. The task seems simple. Look at an image of a galaxy from a massive sky survey and classify its shape. Is it a smooth ellipse, a majestic spiral, or something more peculiar? But within that simplicity lies a profound opportunity. As you scan through these gorgeous, often never-before-seen images, you are training your eye to spot the extraordinary. And sometimes that peculiarity is a cosmic mirage. A volunteer might stumble upon a strange blue arc stretching around a central galaxy, the telltale sign of a gravitational lens. Your click isn't just a classification, it's a potential discovery. Astronomers simply don't have the manpower to visually inspect millions of galaxy images, so the collective pattern recognition power of the crowd acts as an unparalleled filter, flagging the most promising candidates for professional follow-up. This is how amateurs have co-authored scientific papers, helping to find some of the most dramatic lensing systems ever recorded. For those who want to move beyond classification and truly play with the physics itself, sophisticated online simulators offer a digital sandbox for warping spacetime. The Einstein online platform, for instance, features interactive gravitational lensing tools where you can become the master of the cosmos. You can drag and drop your own virtual stars and galaxies onto a grid, then slide a control to increase the mass of a foreground object and watch in real time as the background light begins to stretch and smear. Want to create a perfect Einstein ring? You can adjust the alignment with pinpoint precision. Curious about what happens when a black hole drifts in front of a distant galaxy? You can simulate that too, watching as the entire background field distorts into a swirling vortex around the point of infinite gravity. These tools transform abstract equations into intuitive visual experiences, allowing you to develop a visceral, gut-level understanding of how mass curves space and bends light. It's the difference between being told how a magic trick works and being handed the magician's wand to perform it yourself. The adventure doesn't stop at simulations. NASA Eyes on the Solar System and its more expansive cousin, Eyes on Exoplanets, are freely available software suites that let you pilot a virtual spacecraft through our cosmic neighborhood and beyond. While not solely focused on lensing, they provide crucial context. You can travel to the outer solar system and see how the light from a distant star is minutely deflected by the sun's gravity, recreating the very experiment that proved Einstein's theory. You can then fly to a known exoplanet system, many of which were discovered using the microlensing technique, and appreciate how a fleeting alignment between two stars, one bright, one faint, revealed a world that would otherwise have remained invisible. This software stitches together the tapestry of discovery, showing how different observational techniques, including the study of mirages, combine to build our understanding of the universe. This democratization of astronomy does more than just accelerate research. It fosters a profound shift in our relationship with science. It breaks down the traditional barrier between the expert and the enthusiast, creating a global community of learners and contributors. A retired teacher in Minnesota, a high school student in Nairobi, and a software engineer in Seoul can all be looking at the same data from the James Webb Space Telescope, discussing their findings on project forums, and collectively contributing to a shared body of knowledge. This collaborative spirit enriches education, turning it from a passive transfer of information into an active, social process of inquiry. It also enriches the science itself, injecting a diversity of perspective and thought that can sometimes see patterns and ask questions that a specialized researcher might overlook. By inviting the world to help decode the universe's illusions, we are not just finding more answers, we are cultivating a deeper, more widespread appreciation for the beautiful, deceptive, and endlessly fascinating cosmos we call home. While massive international collaborations and billion-dollar telescopes often grab the headlines, some of the most vital work in hunting for cosmic mirages is done by individuals in their own backyards. The night sky, in its vastness and constancy, is the ultimate democratic laboratory, and amateur astronomers have carved out an indispensable role in this grand endeavor. Their unique strength lies not in accessing the largest instruments, but in something far more valuable: time. Professional observatories operate on tightly scheduled cycles, with astronomers granted perhaps a few precious nights per year on a telescope. This makes it nearly impossible to continuously monitor the sky for the transient, unpredictable events that characterize certain cosmic illusions, particularly the fleeting magic of microlensing. This is where the global network of dedicated amateurs shines, turning their passion into a powerful scientific instrument. Consider the process of a microlensing event. It requires a near-perfect alignment between a distant background star and a faint foreground object, like a dim star or a rogue planet. As the foreground object drifts across our line of sight, its gravity acts as a magnifying glass, causing the background star to brighten smoothly and symmetrically over a period that can last from hours to weeks before fading away just as predictably. Catching the entirety of this event, its rise, peak, and fall, is crucial for determining the mass of the lensing object and whether it might have planets orbiting it. Large survey telescopes like the ones used in the optical gravitational lensing experiment, or OGLE, are fantastic at scanning huge swaths of the sky to find these events as they begin. But they can't watch every single one continuously. The moment an alert goes out that a microlensing event is starting, a worldwide call to arms is issued. This is where the amateur community leaps into action, using increasingly affordable and sophisticated equipment: computer-controlled telescopes, sensitive cooled cameras, and specialized filters set up in suburban gardens or remote rural sites. These enthusiasts can train their instruments on the target night after night. They are not just taking pretty pictures, they are engaged in precision photometry, meticulously measuring the exact brightness of that single star over time. Their data points, contributed to a shared online repository, fill in the gaps between the less frequent observations of the big professional surveys. This high-cadence, continuous monitoring is often the only way to capture the fine details of the light curve, details that can reveal subtle anomalies. A tiny bump on the side of the main brightening event could be the signature of an exoplanet orbiting the lensing star, a world that would otherwise be completely invisible. Some of the most exciting exoplanet discoveries have come from this very partnership, where a professional survey provided the initial alert and a global team of amateurs provided the critical, continuous data that sealed the discovery. Beyond microlensing, amateur astronomers serve as the first line of defense against other transient cosmic illusions. Their regular patrolling of the skies makes them expert noticers, often the first to spot something new or unusual. A sudden brightening in a distant galaxy could be a supernova, whose light might itself be gravitationally lensed by a foreground cluster, creating multiple images of the same stellar explosion. An amateur's vigilant observation and rapid reporting can trigger a global alert, bringing the full power of the world's observatories to bear on understanding the event before it fades. This culture of collaboration is fostered through online forums, social media groups, and organizations like the American Association of Variable Star Observers, which for over a century has coordinated and standardized observations from thousands of volunteers around the globe. In this decentralized network, a retiree in Arizona, a teacher in Germany, and a student in Japan become equal partners in discovery, united by a shared curiosity and a commitment to patient, meticulous observation. Their work proves that the quest to understand the universe's greatest deceptions is not the sole domain of a select few with doctorates, but a profoundly human enterprise powered by passion and a collective desire to peel back the layers of reality. Even with the most advanced telescope ever built on the highest mountain peak, astronomers are forced to do their work while looking through a shifting, shimmering ocean of air. Our atmosphere, that life-giving blanket of nitrogen and oxygen, is the natural enemy of precision observation, a constant source of visual noise that can mimic, mask, or even create its own convincing illusions. This is the first and most persistent layer of deception any ground-based observatory must contend with before it can even begin to decode the universe's deeper tricks. The most common of these atmospheric effects is the one we've all seen on a clear night, the gentle twinkling of the stars. Known scientifically as astronomical scintillation, this romantic flicker is actually the result of turbulence in the upper atmosphere. As starlight passes through countless pockets of air with slightly different temperatures and densities, each pocket acts as a tiny, moving lens, bending the light by a minuscule amount. The cumulative effect is a rapid dance of the star's apparent position and brightness. While beautiful to the naked eye, this twinkling is a form of image degradation for a telescope, blurring fine details and smearing point sources into fuzzy blobs, making it incredibly difficult to detect the subtle, coherent warping of light that signifies a true gravitational lens. To combat this, engineers have developed one of the most ingenious technologies in modern astronomy: adaptive optics. This system is essentially a real-time correction for the atmosphere's distortions. It works by using a powerful laser to project an artificial guide star high in the Earth's mesosphere. This laser star becomes a known, stable reference point. As its light travels back down through the same turbulent air as the celestial objects being studied, its image also becomes distorted. Sensors in the telescope continuously measure these distortions in the laser guide star hundreds of times per second. This information is then fed to a computer that controls a deformable mirror, a mirror whose surface can be altered by hundreds of tiny actuators. The mirror flexes and bends in the exact opposite way to the atmospheric turbulence, cancelling out the blurring effect before the light even reaches the main scientific instruments. The result is an image that can rival the sharpness of those from the Hubble Space Telescope, transforming a fuzzy, shifting view into a crystal-clear window on the cosmos. It's like putting glasses on the entire telescope, allowing it to see through the rippling veil of our own air. Despite this technological marvel, the challenge of atmospheric interference adds a profound layer of complexity to the hunt for genuine cosmic mirages. An astronomer studying a potential weak lensing event must first be absolutely certain that the faint, elongated shape of a distant galaxy is due to the gravity of dark matter and not simply an effect of atmospheric turbulence at the exact moment the image was taken. This requires meticulous statistical analysis, comparing thousands of galaxies in a single field to find a coherent pattern of alignment that defies random chance. Furthermore, the atmosphere doesn't just blur light, it also absorbs specific wavelengths, particularly in the infrared part of the spectrum. This is a major problem for studying the most distant, redshifted galaxies whose light has been stretched into the infrared by the expansion of the universe. From the ground, large portions of this cosmic story are simply blocked, forcing us to rely on space-based observatories to see the full picture. This constant battle against our own planet's air underscores the critical, complementary roles played by ground-based and space-based observatories. Ground-based telescopes equipped with adaptive optics offer immense light-gathering power. Their mirrors can be built to enormous sizes, like the 39-meter diameter extremely large telescope under construction in Chile, allowing them to collect vast amounts of light and study extremely faint objects in incredible detail. They are powerful, flexible, and can be upgraded with new instruments. Space telescopes, on the other hand, enjoy a permanent, pristine view above the atmosphere. They are free from twinkling, atmospheric absorption, and the contaminating glow of city lights. This makes them uniquely suited for the most sensitive, high-contrast observations, like detecting the faint glow of a lensed galaxy right next to a brilliant foreground cluster. The most powerful approach is not to choose one over the other, but to use them in concert. A space telescope like Webb or Hubble might first identify a spectacular gravitational lens, and then a giant ground-based telescope with adaptive optics can perform the follow-up detailed spectroscopic analysis, using its large mirror to dissect the lensed light with precision. This synergy between the clarity of space and the power of the ground is what allows us to peer through every layer of cosmic deception, from the turbulence in our own sky to the warping of space-time at the edge of the observable universe. But who pays for this grand quest to decode the universe's illusions? The breathtaking images from Hubble and the groundbreaking data from Webb represent far more than scientific triumph. They are the products of immense economic investment and complex, often precarious, funding ecosystems. Peering into the deepest reaches of space to study gravitational lensing and cosmic mirages is an endeavor that demands the most advanced technology humanity can build. Massive ground-based observatories with mirrors the size of buildings, exquisitely sensitive instruments cooled to near absolute zero, and satellites that must be flawlessly engineered to operate 1,000,000 miles from Earth. The price tag for this ambition is understandably astronomical, running into the billions of dollars for a single flagship mission. This funding doesn't materialize from nowhere. It is the result of decades of advocacy, international negotiation, and a steadfast belief that understanding our place in the cosmos is a pursuit worth the cost. The financial backbone for this research has traditionally been government space agencies, with NASA, the European Space Agency, and their counterparts around the world leading the charge. Their support is not a blank check. It is earned through a fiercely competitive process where scientists must write detailed proposals, arguing not only for the scientific merit of their ideas, but also for their feasibility and value to the public. This system ensures that only the most robust and promising research gets funded, but it also means that many brilliant ideas for studying cosmic mirages never make it off the drawing board, lost in a sea of competing priorities from planetary science to astrophysics to Earth climate monitoring. The recent rise of private entities in space exploration, like the James Webb Space Telescope's significant contributions from the Canadian and European space agencies, adds a new dimension to this landscape. While primarily focused on commercial ventures, these private efforts are also funding advanced telescopes and may, in the future, provide new avenues for astronomical discovery, though their goals and data access policies can differ greatly from those of public institutions. The argument for continued investment, however, extends far beyond the simple desire to know. There is a powerful economic case to be made, one built on a legacy of tangible returns. The technological challenges of building something like the Hubble or Webb telescopes force engineers to innovate at the very edge of possibility. The solutions they develop rarely stay confined to astronomy. The exquisite sensors developed for space-based telescopes have found new life in medical imaging, leading to more precise MRI and X-ray machines. The software algorithms created to sharpen blurry cosmic images and remove atmospheric distortion are now used to improve everything from satellite weather forecasting to the computer vision systems in self-driving cars. Even the fundamental research into optics and light detection has spun off into countless consumer products. This cycle of innovation creates high-tech jobs, fuels new industries, and generates a return on investment that often far outweighs the initial expenditure, proving that funding fundamental science is also a powerful engine for economic development. Perhaps the most profound, though less quantifiable, return is the inspiration factor. A single image of an Einstein ring from the James Webb Space Telescope can captivate the global imagination, sparking wonder in a generation of future engineers, programmers, and scientists. This is not a trivial outcome. The students inspired by these discoveries today are the workforce that will solve the terrestrial challenges of energy, medicine, and computing tomorrow. Funding cosmic mirage research is an investment in human capital, a down payment on a future built on curiosity and critical thinking. It fosters a culture that values evidence, reason, and long-term exploration over short-term gain. The quest to understand why space tricks us is, at its heart, a celebration of the human spirit's need to explore and understand. It reminds us that we are part of something vastly larger than ourselves, and that perspective alone, though impossible to put on a balance sheet, is a cultural benefit of incalculable worth, uniting humanity under a shared sky full of mysteries waiting to be solved. No single scientist, no matter how brilliant, could ever hope to unravel the universe's grandest deceptions alone. The sheer complexity of a gravitational lensing event, from the initial capture of the distorted light to the final, precise calculation of a dark matter halo's mass, is a puzzle with pieces scattered across countless fields of expertise. This is why the modern quest to decode cosmic mirages is fundamentally a story of collaboration, a symphony of diverse minds working in concert to listen to the subtle melodies hidden within the data. An astronomer might spot a strange, warped arc in a telescope image, but to understand it, they need the theoretical physicist to model the space-time curvature, the data scientist to write the algorithm that analyzes thousands of such arcs, and the computer engineer to build the supercomputers that run the simulations. It is this interdisciplinary fusion that transforms a beautiful curiosity into a quantitative tool, proving that the deepest secrets of the cosmos are only revealed when we break down the walls between our silos of knowledge. Consider the intricate process of mapping dark matter using weak gravitational lensing. The journey begins with the observer, the astronomer who pilots a massive telescope, carefully collecting the faint light from millions of distant galaxies over countless nights. This raw data is then handed to the data scientist, who must first clean it, removing the artifacts introduced by the telescope's own electronics and the subtle distortions from our atmosphere. They then apply sophisticated statistical algorithms to measure the tiny, coherent distortions in the shapes of those background galaxies, a signal so faint it is completely drowned out by noise until you apply the right mathematical filters to billions of data points. This processed map of distortion is then passed to the theoretical cosmologist, who uses it to run immense computer simulations. They test countless models of how dark matter might behave. Is it cold or warm? Does it interact with itself, iterating until their simulated universe produces a pattern of distorted light that perfectly matches what the observer actually saw? Finally, a philosopher of science might be brought in to help interpret what it all means for our understanding of reality itself, questioning the assumptions embedded in the models and the nature of the knowledge being produced. This entire pipeline, from photon to philosophy, is a chain of specialized expertise, each link utterly essential to the final result. This collaborative spirit is physically embodied in the way modern observatories are run. Large projects like the Vera-C, Rubin Observatory, or the Laser Interferometer Space Antenna are not the work of a single institution but massive international consortia involving hundreds of scientists from dozens of countries. Their weekly collaboration meetings are a microcosm of this interdisciplinary dance. An observer might present a new, puzzling image, prompting a lively debate where a particle physicist suggests a new dark matter model. A computer scientist proposes a novel machine learning approach to analyze it, and an engineer works out the feasibility of a new observation strategy. This constant cross-pollination of ideas is a powerful engine for innovation. A technique developed to clean up cosmic microwave background data might be adapted by a medical researcher to improve brain scan imagery. An algorithm created to find gravitational lenses might become the foundation for a new facial recognition system. By working together on the universe's biggest puzzles, we inadvertently develop the tools to solve some of our own. There's a moment that often arrives after the initial thrill of understanding a cosmic mirage, a quiet personal shift that has less to do with galaxies and more to do with the person staring up at them. Discovering that the universe is not just a static backdrop but an active participant, a grand illusionist warping light and time, does something profound to the human psyche. It can feel like learning the secret to a magic trick you've marveled at your entire life, only to realize the truth is far more astonishing than the illusion itself. This realization often evokes a deep and resonant sense of awe, a feeling that psychologists have even given a name: cosmic awe. It's that specific blend of wonder and humility that comes from confronting something vastly greater than yourself, something that simultaneously expands your perspective and makes you feel beautifully small within the grand scheme of things. This isn't a frightening smallness, but a connecting one, a feeling that you are a conscious part of an incredible, dynamic, and intelligible universe. For many, this experience is overwhelmingly positive, sparking a powerful sense of curiosity and intellectual adventure. It's the feeling that drives amateur astronomers to spend cold nights patiently guiding their telescopes, or compels a student to dive headfirst into the complexities of physics. Learning that dark matter, an invisible substance we can never directly see, sculpts the light we observe, reinforces a thrilling idea. The universe is not just a collection of pretty lights, but a complex, logical puzzle that can be understood through patience and reason. This engagement is deeply fulfilling. It transforms our relationship with the cosmos from one of passive observation to active inquiry, providing a powerful antidote to the everyday concerns that can often dominate our minds. The vastness of space becomes not a void of indifference, but a canvas for exploration, inviting us to learn its rules and appreciate its artistry. Yet, the same vastness that inspires wonder in some can trigger a very different response in others, a feeling often described as existential anxiety or cosmic dread. The idea that our reality is malleable, that our senses can be so easily deceived on a universal scale, can feel deeply unsettling. It challenges the very foundation of a stable, objective world, suggesting that even the most constant things we know, the fixed positions of stars, are ultimately a matter of perspective. This can lead to a disorienting sense of disbelief, or even a feeling of insignificance that is isolating rather than connecting. When the universe is revealed to be so strange and so immense, it's natural to question our place within it. These are not irrational fears, but a logical human reaction to having our most fundamental assumptions about reality gently but firmly dismantled. This duality of responses is precisely why understanding the psychology behind these discoveries is so crucial for scientists and communicators. Sharing these breakthroughs isn't just about relaying facts and figures, it's about telling a story that acknowledges both the head and the heart. The most effective communication frames these concepts not as cold, abstract truths, but as part of a grand, ongoing human adventure. It means pairing the image of an Einstein ring with the story of its prediction a century ago, highlighting the enduring human curiosity that bridged the gap between a mathematical idea and a confirmed reality. It involves using thoughtful analogies that ground these colossal concepts in relatable experiences, helping to build a bridge of understanding over what might otherwise feel like an intimidating chasm of complexity. Ultimately, our fascination with cosmic mirages reveals a fundamental truth about humanity. We are meaning-making creatures. We look at the chaos of the night sky and instinctively search for patterns, for stories, for understanding. The fact that the universe often plays tricks on us in this pursuit doesn't discourage us. It deepens the mystery and makes the eventual understanding all the more rewarding. These psychological journeys, from wonder to anxiety to a more nuanced appreciation, are an essential, humanizing part of the scientific process. They remind us that every new discovery about the cosmos is also, in a way, a new discovery about ourselves and our endless capacity to confront the unknown with a mixture of trepidation and awe. Sometimes the universe stages the perfect experiment, a cosmic event so clear and dramatic that it cuts through decades of debate and delivers an answer with breathtaking clarity. This is precisely what happened with a system known officially as 1E0657-558, but which earned a much more dramatic nickname, the Bullet Cluster. Located about 3.7 billion light-years away, it is the aftermath of a violent, high-speed collision between two massive galaxy clusters, a cosmic car crash unfolding on an unimaginable scale. For astronomers, this wasn't just a spectacular sight. It was a natural laboratory, a controlled experiment that provided what many consider to the most direct and compelling evidence for the existence of dark matter. To understand why this collision was so revealing, we need to think about what happens when two clusters smash together. Each cluster is made of three primary components: the galaxies themselves, which are vast collections of stars, a huge cloud of superheated gas that fills the space between the galaxies, and an immense, invisible halo of dark matter that makes up the vast majority of the cluster's total mass. During a collision, these three components behave in strikingly different ways. The galaxies within each cluster are mostly empty space. When two clusters collide, the galaxies, like swarms of bees, largely pass right through one another without interacting, their gravitational pulls gently shepherding them along. The clouds of hot gas, however, are a different story. This gas is a tangible, interactive substance. As the clusters collide, the gas clouds from each one slam into each other, much like two clouds of smoke would in a slow-motion film. This collision creates immense friction and pressure, slowing the gas down dramatically and heating it to even more extreme temperatures, causing it to glow brightly in X-ray light. This glowing gas becomes stuck in the middle of the collision. But what about the dark matter? By its very definition, dark matter does not interact with light or with ordinary matter through any force other than gravity. It doesn't feel friction or pressure, so during this colossal collision, the dark matter from each cluster should behave just like the galaxies. It should simply coast right through the aftermath, completely unaffected by the gas collision. This is the critical prediction, but how could we possibly test it? We can't see the dark matter. This is where gravitational lensing provides the key. Even though dark matter is invisible, it has mass, and its gravity warps the fabric of spacetime. By meticulously mapping the gravitational lensing effects around the bullet cluster, by measuring how the light from more distant galaxies is distorted, astronomers could create a precise map of where the total mass actually is. When the results came in, the image they painted was stunningly clear. Observations from the Chandra X-ray Observatory showed the telltale signature of the gas collision: two bright, bullet-shaped lobes of multimillion-degree gas that had been slowed and piled up in the center of the system. But the mass map, derived from Hubble Space Telescope observations of gravitational lensing, told a completely different story. The peak of the mass distribution was not with the gas in the center. Instead, it was located in two distinct clumps that had sailed cleanly through the collision site and were now far out in front of the trapped gas. These clumps of mass were perfectly aligned with the positions of the galaxies that had also passed through. The inescapable conclusion was that most of the matter in the clusters was not where the visible matter was concentrated. It was located in these separate, invisible halos. The gas, which represents the majority of the normal matter, had been separated from the majority of the total mass. The only thing that could account for this missing mass behaving in this frictionless way was dark matter. The bullet cluster evidence was so powerful because it ruled out alternative explanations for the missing mass. Some scientists had proposed that perhaps we simply didn't understand gravity correctly on large scales, and that modifying our theory of gravity could account for the observations without invoking an invisible substance. But the bullet cluster presented a scenario that modified gravity theories struggled to explain. If the problem was with gravity itself, the lensing map should have shown the mass where the bulk of the matter, the gas, was located. The fact that the mass and the gas were in completely different places was a direct demonstration that most of the matter was not only dark, but that it truly was a collisionless, ghostly substance that interacted with the rest of the universe almost solely through the force of gravity. It was a direct detection of dark matter's gravitational influence, even as the substance itself remained utterly hidden from view. This single, elegant cosmic experiment transformed dark matter from a compelling theoretical idea into an inescapable component of our physical reality, all thanks to the power of gravity's greatest trick. Think of our best models of the universe as incredibly detailed and complex maps. They chart everything from the explosive birth of the cosmos in the Big Bang to its ultimate fate, describing how galaxies form, how dark matter weaves its invisible web, and how dark energy drives the accelerating expansion of all space. But a map is only as good as its ability to match the actual terrain. For cosmologists, that terrain is the observable universe, and for decades, our most precise tools for surveying it have provided conflicting measurements for one of the most fundamental features on the map, the universe's current rate of expansion, known as the Hubble constant. This discrepancy, famously called the Hubble tension, is arguably the most pressing puzzle in modern cosmology. On one side, we have meticulous measurements from the early universe, primarily from the Planck satellite's observation of the cosmic microwave background, which provide one value for the expansion rate. On the other side, we have measurements from the local, modern universe using pulsating stars called Cepheid variables and cataclysmic stellar explosions, known as Type Ia supernova, which consistently give a higher value. It's as if two of the most reliable rulers ever built disagree on the size of the same object. This tension suggests that either one set of measurements contains an unaccounted for error, or, more excitingly, that our standard cosmological model is incomplete and we are on the verge of discovering new physics. This is where cosmic mirages move from being fascinating curiosities to indispensable scientific instruments. Gravitational lensing provides a completely independent and powerful third ruler for measuring cosmic distances, one that relies on the pure geometry of spacetime itself rather than the properties of stars. The technique involves a specific and precious type of lensing event where the background object is not a static galaxy but a variable quasar, a brilliantly flickering active galactic nucleus. Because the light creating each of the multiple images of this quasar takes a different path around the lensing galaxy, each path has a slightly different length. This means when the quasar suddenly flares in brightness, that flare doesn't appear in all the mirrored images at the same time. It will appear in one image, then days or weeks later in another. By patiently monitoring these systems for years, astronomers can measure these time delays with exquisite precision. These time delays are like a cosmic stopwatch. they provide the critical data needed to reverse engineer the entire geometry of the system. Combined with a measurement of how the lensing galaxy bends the light, this allows scientists to calculate an absolute distance to both the lens and the source, providing a direct one-step measurement of the Hubble constant that is free from the long chain of assumptions that other methods require. The results from these lensing time delay studies are beginning to weigh in on the Hubble tension, and they are delivering a fascinating verdict. Large collaborative projects like the H0LICW collaboration and its successor, TD-COSMO, have meticulously analyzed several of these systems. Their measurements of the Hubble constant have consistently fallen right in between the values from the early universe and the local universe, though they often show a slight preference for the higher values from the local measurements. This independent confirmation from an entirely different physical phenomenon is a monumental achievement. It tells us that the tension is almost certainly real and not just a systematic error in one method. The mirages are acting as a referee in a high-stakes debate, confirming that the discrepancy is a genuine feature of our cosmos that demands an explanation. This forces cosmologists to seriously consider revisions to the standard model, perhaps involving exotic new properties of dark energy, interactions between dark matter and dark radiation, or other physics beyond our current understanding. Beyond resolving the Hubble tension, gravitational lensing serves as a natural laboratory for testing the very fabric of gravity and the nature of dark matter on colossal scales. The precise shapes of Einstein rings and the statistics of how thousands of galaxies are weakly lensed are exquisitely sensitive to how matter is distributed throughout the universe. This distribution is governed by the relentless pull of gravity and the counteracting push of dark energy. Different theoretical models for dark energy predict different expansion histories for the universe, which in turn affect how quickly cosmic structures like galaxy clusters can form over time. By counting how many strong gravitational lenses exist at different cosmic epochs and measuring their properties, astronomers can determine which expansion history best fits the data. Is dark energy a constant force as represented by Einstein's cosmological constant, or does its strength vary over time? The abundance and strength of cosmic mirages across the history of the universe provide a crucial observational test. Furthermore, the way dark matter clumps on the smallest scales within these lenses can be probed by looking for subtle anomalies in the lensing patterns, offering clues about whether dark matter is cold, warm, or perhaps even self-interacting. Each distorted image is a snapshot of gravity in action, a data point that helps refine the equations on our cosmic map. This iterative process of observation and refinement is the very engine of scientific progress. A cosmological model makes a prediction, for instance. It predicts how many large galaxy clusters should exist at a certain distance. Astronomers then use gravitational lensing to conduct a census, measuring the masses of these clusters and counting them up. If the observation disagrees with the prediction, the model must be revised. Perhaps the nature of dark energy needs to be tweaked, or the properties of neutrinos need to be adjusted. The updated model then makes a new prediction, which is again tested against fresh observations of cosmic mirages. This continuous feedback loop, powered by the universe's own deceptions, ensures that our models remain grounded in observable reality. The illusions are not a hindrance to understanding, they are the very mechanism through which we achieve it. They force our theories to evolve, to become more robust, and to more accurately reflect the beautiful, complex, and often deceptive cosmos we are so privileged to study. Of course, one of the most common mix-ups happens when a stunning image of a gravitational lens makes the rounds online. Someone might see a perfect Einstein ring or a strange blue arc warping around a galaxy cluster and immediately jump to the conclusion that it must be evidence of something artificial, a UFO of unimaginable scale, or perhaps even a structure built by an advanced alien civilization. It's a thrilling thought, but the reality, while perhaps less sci-fi, is infinitely more profound. These are not constructions. They are the natural, predicted consequences of gravity warping space-time, a phenomenon that follows the precise mathematical rules set down by Einstein over a century ago. The universe doesn't need an architect to build these wonders. It has physics, and that is more than capable of creating sights that dwarf our wildest imaginations. The true wonder isn't in imagining a mysterious builder, but in understanding that the cosmos operates by laws we can comprehend, predict, and ultimately use to unravel its deepest secrets. This confusion often stems from a fundamental misunderstanding of the word illusion itself. In everyday language, an illusion often implies a trick, a deception meant to fool you, like a magician's sleight of hand. But in a cosmic context, a mirage is not a lie, it is a translation. It is the universe faithfully following its own rules, and our job is to learn how to read the output correctly. The light is not being deceptive, it is being obedient. It is following the curved geometry of space dictated by the mass it encounters. When we see multiple images of a single quasar, the light isn't trying to trick us. It is honestly reporting the different paths it was forced to take on its long journey to our telescopes. The deception is only in our initial, uninformed interpretation. Once we understand the rules of the road, the laws of general relativity, the illusion vanishes, not because the effect goes away, but because we finally see the truth hidden within the distortion. It transforms from a confusing puzzle into a precise measuring tool. Another persistent myth is the idea that these effects are somehow supernatural or paranormal, a sign of forces beyond scientific understanding. This is perhaps the most important misconception to address, because it draws an artificial line between the awe-inspiring and the explainable. The breathtaking beauty of an Einstein ring does not lose its power or its majesty when we understand the physics behind it. In fact, it becomes even more magnificent. Knowing that this perfect circle of light is the result of a precise alignment of mass and energy across billions of light years, exactly as predicted by a theory that reshaped our conception of reality, adds a layer of depth and wonder that pure mysticism could never provide. The supernatural explanation actually sells the universe short. It replaces a deep, evidence-based understanding with a shallow mystery, trading a truly awesome reality for a mere ghost story. Science doesn't remove the wonder, it gives that wonder a foundation and a context, allowing us to appreciate not just the what, but the sublime how and why. Our own human psychology also plays a role in fueling these misconceptions. We are hardwired pattern recognition machines, a trait that has been essential for our survival. But this same useful instinct can lead us astray, causing us to see familiar shapes and intentional designs in random astronomical data, a phenomenon known as pareidolia. This is why some people might look at a nebula and see a face, or examine a Martian rock formation and perceive a sculpture. It's a completely natural cognitive shortcut, but it becomes a problem when we mistake this initial, subjective perception for objective analysis. The scientific process is specifically designed to counteract these innate biases. It demands evidence, peer review, and reproducibility. So, while it's fun to see a celestial horsehead or a crab in the clouds of gas, science pushes us to move beyond that initial impression and ask the quantitative questions. What is its composition? What are its dynamics? How did it form? This shift from pattern recognition to physical analysis is what separates casual speculation from genuine discovery. Addressing these myths is not just an academic exercise, it is a crucial part of fostering a scientifically literate society. In an age of rampant misinformation, the ability to critically evaluate a claim, to ask for evidence, and to understand the difference between a scientifically supported phenomenon and a baseless conspiracy theory is more important than ever. When we take the time to explain that a cosmic mirage is a natural effect with a known cause, we are doing more than just sharing a cool astronomy fact. We are reinforcing a worldview that values evidence, reason, and intellectual humility. We are empowering people with the tools to navigate a complex information landscape, not just in astronomy, but in every aspect of their lives. It ensures that the public's sense of awe, which is so powerfully ignited by these cosmic deceptions, is directed toward a genuine appreciation of science and the natural world, rather than being misdirected into the cul-de-sac of pseudoscience. This careful, respectful communication ensures that the universe's greatest tricks are understood not as mysteries to be feared, but as invitations to learn, explore, and be humbled by the magnificent reality we are so fortunate to inhabit. There is a moment experienced by nearly every astronomer when a new image first resolves on the screen. The data has been collected, the algorithms have processed the raw photons, and there it is, not just data, but a picture. A perfect Einstein ring, a halo of radiant light encircling a distant galaxy cluster, or perhaps a distant quasar, its image split into a delicate cross by the gravity of an unseen hand. In that moment, the initial reaction is rarely a cheer of scientific triumph. It is often a stunned, breathless silence, a whispered, "Wow." This involuntary response points to a truth that is sometimes overlooked in the rigorous world of data and equations. The pursuit of knowledge is not a purely intellectual exercise. It is also an aesthetic one. The most profound cosmic mirages are not just correct, they are breathtakingly, achingly beautiful. And this beauty is not a happy accident. It is a fundamental part of their power to captivate, inspire, and ultimately reveal the deep structure of reality. This aesthetic appeal is the most potent gateway for public engagement with complex science. A dry graph charting the density of dark matter might earn a respectful nod from a specialist, but a Hubble image of a galaxy warped into a brilliant blue arc stretching across the void. That stops everyone in their tracks. It bypasses the need for advanced degrees and speaks a universal language of wonder. This visual splendor draws people in, creating a moment of shared awe that transcends cultural and educational boundaries. It makes the abstract tangible and the distant immediate. A parent and child can look at the same image of a gravitational lens and for a moment share the same sense of mystery and grandeur. This emotional connection is the hook. It creates the curiosity that leads to questions, and those questions are the very foundation of scientific literacy. The beauty of the image becomes an invitation to understand the physics behind the poetry, transforming passive observers into active learners hungry to know how such a thing is even possible. But is this link between beauty and truth merely a psychological trick, a way our brains reward us for engaging with the world, or does it point to something deeper about the universe itself? Many of the greatest physicists in history, from Einstein to Dirac, have spoken of their intense reliance on a sense of mathematical beauty to guide their work. They believed that the correct theory, the one that truly describes nature, would also possess a certain elegance and simplicity. The equations of general relativity, from which the entire phenomenon of gravitational lensing springs, are a prime example. They are complex, yet they possess a profound symmetry and economy. They describe a universe where the force of gravity is not a mysterious pull, but a natural consequence of mass telling spacetime how to curve, and curved spacetime telling mass how to move. This is a beautifully coherent idea. The stunning visual manifestations of this theory, the Einstein rings, the arcs, the crosses, are simply the physical expression of that underlying mathematical elegance. The beauty we see with our eyes is a direct reflection of the beauty inherent in the universe's operating system. The cosmic mirage is the artwork, general relativity is the elegant brushstroke. This relationship suggests that our human sense of aesthetics might be more than just a feeling. It might be a tuned instrument refined by evolution for detecting order and pattern in the world. When we encounter something we perceive as beautiful, whether it's a sunset, a symphony, or a spiral galaxy, we are often responding to an underlying harmony, a resolution of complexity into a satisfying whole. A gravitational lens presents us with a seemingly chaotic distortion, a galaxy that looks like a stretched piece of taffy. But when we apply the rules of general relativity, that distortion resolves into a perfect, predictable pattern. The chaos was an illusion. The order was there all along, waiting to be decoded. Our sense of beauty seems to resonate with this deep-seated order, guiding scientists toward theories that have the ring of truth. It is the emotional spark that fuels the long, often tedious labor of verification. Celebrating this dimension of science is a vital antidote to the sterile perception of it as a cold, purely rational enterprise. It reminds us that the drive to explore the cosmos is fueled by the same human emotions that drive us to create art, compose music, or write poetry: curiosity, wonder, and a deep desire to find meaning and connection. The scientist at the telescope and the artist at the canvas are both engaged in acts of discovery, trying to reveal something true about the world and our experience of it. By openly embracing the beauty of our discoveries, we make science more human, more accessible, and more inviting. We acknowledge that the pinnacle of scientific achievement is not just a dry paper in a journal, but that gasp of wonder, the moment when a new piece of the universe's puzzle clicks into place with such grace and brilliance that it feels less like a calculation and more like a revelation. The cosmic mirage, in all its sublime glory, stands as the ultimate testament to this beautiful truth. As we bring our journey through these cosmic deceptions to a close, it's worth pausing to reflect on the extraordinary path we've traveled together. We started by considering the simple yet profound nature of light itself, a messenger from the distant cosmos whose journey is anything but straightforward. We then witnessed how Einstein's brilliant intuition, once just a curious prediction scribbled on paper, blossomed into the observable reality of gravitational lensing, allowing entire galaxies to act as nature's own telescopes. We marveled at the precise categories of this phenomenon, from the dramatic arcs of strong lensing to the subtle statistical shearing of weak lensing and the transient brightening of microlensing, each a unique window into the unseen. We stood in awe before the perfect geometry of the Einstein cross, a celestial alignment so precise it feels almost designed, and we felt the ripples of gravitational waves, a confirmation that space-time itself is a dynamic fabric that can stretch and compress. We ventured into the realm of the invisible, tracing the gravitational influence of dark matter as it sculpts the cosmos's largest structures and crafts its most elaborate illusions. We peered into the abyss around black holes, where gravity becomes so intense that it creates photon spheres and shadows, warping our view of the universe into a dizzying vortex. We grappled with the enigmatic push of dark energy, a force that alters the very expansion of the universe and thus changes how we interpret every mirage we see. We learn to distinguish these true cosmic deceptions from the more local tricks played by our own atmosphere and the inherent biases of our own perception. And we celebrated the incredible tools, from Hubble's crystal-clear vision above the atmosphere to Webb's infrared eyes peering back to the first light, that have transformed these theoretical curiosities into precise instruments of discovery. This entire voyage underscores a single, powerful idea that our universe is not a static stage. It is a dynamic, interactive, and often deceptive participant in the quest for understanding. The cosmic mirage is not a flaw in the matrix or an error in observation. It is a fundamental feature of a cosmos governed by gravity and relativity. These illusions are the universe's way of revealing its secrets indirectly. We cannot see dark matter, but we can see how its gravity bends light. We cannot see a black hole, but we can photograph the shadow it casts against illuminated gas. We cannot feel the expansion of space-time, but we can measure how it changes the effectiveness of gravitational lenses over cosmic time. The greatest tricks are, in the end, the most honest clues. So the next time you find yourself under a clear night sky, take a moment to look up. Remember that the light arriving at your eye has traveled for years, decades, or millennia across a universe that is anything but empty. It has been nudged, stretched, magnified, and redirected by the invisible hand of gravity acting upon the fabric of space-time. That pinpoint of light you see might not be where you think it is. That faint smudge might be an entire galaxy warped into a ring by an invisible halo of dark matter. Reality is not a fixed picture. It is a fluid, malleable experience, and our perception of it is just a single frame in an infinitely complex and beautiful film. This perspective is perhaps the most valuable gift of astronomy, not just a collection of facts, but a profound sense of humility and wonder. It is an invitation to remain curious, to question everything, and to always look for the deeper reality hidden just beyond the illusion. The cosmos is the greatest magician of all, and its greatest trick is convincing us there's nothing more to see. But now we